first part of air conditioning is air, and we've got to get the airflow right. You remember the old 67 Chevys? You know, you used to be able to pee in the carburetor and everything would work forever, right? It did, and now you get a drop of moisture in and everything shuts down. So that's what's happening more and more with our air side of our systems now. And if we keep doing what we used to do, it just ain't gonna fly anymore. So we're gonna have to change up the way that we've been doing it. So I need to first find out you guys have the app on your phone, the Coburn's Connect app. Okay, I need to make sure that y'all all have access to it and can get into it, because we're gonna talk about a lot of those different calculators today. And I want to make sure that you have access to it, but I want to make sure that you know how to get in there and find what I'm talking about, because this is going to save you a lot. Because all these papers, all the duct calculators, you're up in the attic, and where's all these papers? They're out in the truck. Where's your phone? You got that, right? You always going to have that. So with that, I just need to make sure that you have all the information you need right with you in your pocket. The tools I'm going to show you on these calculators are going to be invaluable when you're out on the job site. And I just want to make sure that you're with me throughout this, because I'm going to give you the long division today, and then I'm going to say, oh, look, we got a calculator for that. Guys, airflow is going to be everything going into the very near future. We were just talking about having all of the problems with moisture on these jobs. Moisture is going to be a huge part of it. Who sets the speed on these units when you guys start them up? Who set? You set it. So it didn't come set from the factory? Mm-hmm. What? I thought the factory knew everything. They don't know what we're putting out there. They don't know what we're hooking it on to. Hey, Dave. They don't know what we're putting all this stuff on. So they're gonna count on us to put it together and make the airflow right. So we're going to talk a lot about airflow here today. Air distribution is more than just, it's blowing real good, because when I get calls from you guys out there in the field and I'm saying, hey, what's going on this job? What's the airflow like? Oh, it's blowing real good. I don't know really what that means. I mean, I need to know quantity, I need to know speed, I need to know whether the air is clean, whether it's noisy, what's the pressure differential, what's the static pressure, the leakage, is the ductwork's all leaking on the supplier return, the thermal infiltration or exfiltration, does it have insulation on it? Is it wrapped well, or is it that old paper wrap stuff that basically has no insulation on it at all? So we're going to have to know what's going on with that distribution system, and it's more than it's just blowing real good. So I'm old, so every time I go to the doctor, the first thing he does is slap that blood pressure cuff on me, and he checks my high side and my low side with that every time. So that's our gauges, right? So the other thing he does is he takes that stethoscope, he puts it on my back, and he says, breathe in, breathe out. So he's checking my airflow. So we're checking the refrigerant side, and then we have to check the airflow. And how do we check the airflow? With the handometer, right? Yeah, we move the handometer and say, okay, well, yeah, it's blowing real good. Well, I'm telling you this here, guys, that hasn't been calibrated in years. You guys have not done it. You don't know whether it's moving right. So what we're seeing is we've got a lot of people out there very confused about the difference in quantity of air, CFM, and velocity, the speed of air as it's coming out. So you put your hand up there and you say, oh, it's blowing real good, right? Oh, it's blowing real good. When you have to go change ductwork because it's undersized or it's all running in different directions or what have you, when you guys do that, the homeowner is going to say, oh, $10,000 to change out my ductwork? What are they going to do? It's blowing real good. We've taught them how to use the handometer. We have to step up our game. We have to go above and beyond something that we used in the 1960s. We have to step up our game, use the tools to accurately calculate the airflow and move forward, because right now we've got a bunch of bad duct work out there that's not moving the air that we need it to move, and we have to do a better job on the front end so we're not having to go back out on a recall. How much does a recall cost? Do you know?
That he does.
Every time you go back on a job that's a recall because we didn't get it right the first time, it cost us about $225. $225 every time. How many times have you guys been out on some of these jobs? Yeah. How much do you think we actually made on that job? I'm thinking at some point in time, it would have been better for us to write the customer a check for $50, $100 and say, don't call me. So we have to, on the front end, make sure that we have everything accurate and we've checked it out, and then we'll go start it up. And we'll show you what to do as we start getting that system up and running. Fair enough? Cool. All right. Well, how important is airflow?
Very important.
Very important, yeah. How important is the ductwork sizing?
Very
Yeah. How important is the return air grill sizing?
important.
Yeah, very important. So here's how we're going to prove that out. I want you to, you're a young, strong man, I want you to jog around the block. You come back and your heart's going, and then your lungs are going, 95-degree day. You're working hard, right? But your compressor is working, and your lungs and your blower's working really good. This time, when you get back, I want you to hold one nostril shut, just one nostril. You can still breathe through your mouth, you can breathe through your nose, you can do everything you want. Just hold one nostril shut and jog around the block again. What's your heart going to be like when you come back that time? You only had a slight restriction, just a small restriction. But how's your heart going to be beating when you get back this time?
Rapidly.
Good. So what you're telling me is your airflow side of your system and your compressor side of your system have to work together. And when I restrict the airflow, it directly impacts my compressor. A customer gets that. So when they say, how come the old system used to work fine, it did very well, and now I have to start changing ductwork? Because everything is more fine-tuned now. Just like your automobile, everything is more fine-tuned. They can understand what happens when you have restrictions in your ductwork if you just use that type of an analogy. Does that make sense? You start going, well, the static pressure is high, and with the static pressure high, it's going to reduce that CFM and increase that velocity. What are they hearing? Wow, 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 wow. They don't understand. And you're just talking over their heads. So bring it down to where they can understand it, and the world's going to be a lot better. Fair enough? Cool. All right. So the compressor is broken, right? The compressor is broken, and you're going to put in the new super duper 45 SEER, whatever the hell it is. If you do that and apply that right on that asthma-ridden duct system, do you think you're going to get anywhere near the super duper 45 SEER, whatever the hell it is? No, you're not. Because you put it on an asthma-ridden duct system that can't breathe.
Not compatible.
Not going to work. Not going to work. So what do we have to do if I'm going to put in the 45 SEER super duper whatever?
Upgrade to that.
Da-da-da-da. Da-da-da-da. So every time you guys go do maintenances on all of these systems that are old, and you come off of there and the homeowner says, well, how's it doing? Oh, it's doing okay. It's doing all right. Did you ever talk about the duct system? Because when there's going to come a time, they're going to have to change it out, right? And you didn't even warn them about the duct system. You never even talked to them a little bit about the duct system. Are they even thinking they're going to have to change the duct system out? It's doing as good as it can for right now for its age. It's really not doing great, but it's doing, you know, you're keeping along. But listen, when you start to go upgrade this system, because I know that's in y'all's near future, when you do that, you really need to look at the duct system as well. Because the duct system is, number one, undersized. It's uninsulated. I saw leaks all throughout the system. It's just got to the end of its useful life. Now are we giving that customer some information. Cool. Now it's not, okay, well, I can spend $10,000 on the AC, but I can still go on my vacation to Florida or whatever. Now they're starting to figure out, okay, well, I got to start putting more money away for that too. Does that make sense?
Yeah.
Prepare them for it. Cool? All right. So let's talk about what it is. And when we talk CFM, I found out there's a lot of guys really didn't get a handle on this. CFM is a cubic foot of air in a minute. So if I take this 1 cubic foot of air and move it across an evaporator coil in 1 minute's time, that is 1 CFM. Okay? So we typically have about 400 CFM for every ton of air. Is that right? 400. So if I take a 10 foot by 5 foot room, maybe the size of the bathroom, 8 foot tall, that's 400 cubic feet. So every minute, I'm going to move a bathroom's worth of air across the evaporator coil in 1 minute's time. Does that make sense? Good. So let's take it one step further. Let's do 4 tons. 4 tons is 1,600 cubic feet. That would be a 20 foot by 10 foot room, 8 foot tall. Every minute, I'm going to move this living room worth of air across that evaporator coil in 1 minute's time.
Rick, if I'm not mistaken, that is pretty close to the size of this room
Okay?
we are in right now.
Okay, so every minute, this is what you're going to move across that evaporator coil. Now tell me this, can I do that through an 18-inch duct? Stop and think about it. I'm taking this. It's like making boudin this big. You can't get this much air through this size duct. It's physically impossible. Do you get that? So that's what I'm talking about on cubic feet of air. We have a volume of air that needs to move through that duct. And just because it's moving through doesn't mean it's moving through effectively. Everybody cool with that? Good. All right. So total CFM is dependent on 2 things. The pressure blowing it, and that's the guy at the factory who designs that blower. He says, if I take this motor, this horsepower, with this size blower wheel, and turn it this fast, I'm going to get this much CFM if you guys give me a little bit of resistance on the ductwork. So that's the second part. The size of the ductwork and fittings. If he's building for this size ductwork and you give him this size ductwork, what's not going to come out? The CFM. Does that make sense? So we got 2 things that are dependent. The guy that assumes that you're going to size it right and you to size it right. Everybody good? Sweet. Because the engineer controls the blower design, this only leaves you the ability to be able to make the other things happen. And that's the fittings, the duct, and how it's actually physically run. Duct system pressures. We have 3 pressures typically out there in the system. You have static pressure, which is pressure in all directions. Velocity pressure, that's the speed is going down the middle. And total pressure is the combination. We don't typically look at a whole bunch more than static, but I want to explain static and velocity because I think they're important on how the system operates. So, static pressure. It exerts force in all directions. So, inside that duct, static pressure is pushing this way, this way, this way. When you get a lot of static pressure in that ductwork, what does the ductwork do? Right? You've heard it? Even on the return side, you have it and it goes, yes? So that's static pressure. It's pressure in all directions. But look, it's not just out. Static pressure is pressure this way too. Pressure in all directions. So if I'm pushing this way with static pressure, and airflow is coming this way, what's the static pressure doing?
Resistance.
It's the resistance to airflow. It is absolutely the resistance to airflow. So the higher the static pressure I have, closing off the grills, if I close off the grills, that static pressure is going to go, yes? What's it going to do to airflow?
Chill.
Does that make sense? Good. All right, so static pressure is pressure in all directions. Static is resistance. Static is the opposition to CFM. Velocity pressure. That's a little different. Velocity pressure doesn't like the edges. Velocity pressure is lazy. Velocity pressure just wants to run right down the middle of the duct. I don't want to touch the sides. I don't want to do any of that. I just want to go right down the middle and just don't bother me. I'm going to just go in one direction. This is my job. Well, that's all fine and good. It's going to run down the middle. It doesn't hit the sides. It doesn't do anything until you turn that duct. And when you turn that duct, that velocity is going straight down there, and it said, oh, don't bother me, until it hits the turn. And then it starts hitting on the side. It starts rolling around. And then it bounces off to this side and comes back. What is that doing when I have all of that air hitting all of those walls?
Slowing it down.
Slowing it down. It's resistance. Resistance. So tell me, Hunter. It blows out the blower to the plenum, turns directly around, and has to start heading back, and then it has to do some of this and over there. What did we do to the velocity pressure inside that ductwork? Increased it, right? Increased it. What did it do to the CFM in that ductwork?
Decrease.
There it is. You got it? What if I just, instead of having a 90, what if I had a 45?
Less resistance.
You follow? What is it going to do to the airflow?
Better.
Does that make sense? Good. So understanding the velocity pressure and the static pressure, two different things. Velocity feet per minute. This is the speed at which the air is flowing. Now, this is where your handometer has been lying to you for years. Because technicians typically make the mistake that air moving quickly is large quantities of air. Because if that grill was blowing, and it was blowing stuff off of this desk, you would say, oh my goodness, I'm moving a lot of air. You're not. You're moving a small amount of air very quickly. So let's see. 2 cubic feet of air in my lungs. Okay? 1 cubic foot, 2 cubic feet. If I move it through a large duct, I can move it very quickly, very efficiently. 2 CFM. Did you follow that? Let's take that same 2 CFM and move it through a small duct. Did it take longer to move the same 2 CFM? So my velocity increased, my speed of my air increased, but the quantity didn't move out near as fast. Watch. You see what I'm saying? Which one are you feeling with your hand?
You feeling it?
So you're not feeling the quantity of air, you're feeling the velocity, is that right? So what we've been saying now is that all you're feeling is the air moving fast, but you have no idea how much air is coming out. Does that follow? You follow me on that? Okay, cool. So technicians typically make the mistake that air moving quickly is large CFM. That's not right. This answers the question of why heat pumps blow cold air. You've heard the customers complain, I hate heat pumps because they blow cold air. I'm here to tell you, no, it's not. It does not blow cold air. You've got your ductwork undersized. Let's prove that out. What's the temperature of the air in your lungs? 98 degrees? Okay. Let's take 98 degree air and move it through a large duct onto the back of your hand. Come on, you guys can do this. Come on. What you got? Warm air?
Yeah.
Take that same 98 degree air, move it through a small duct onto the back of your hand. It's 98 degree air. It's still 98 degree air. All we did was change the speed at which that air was coming out, didn't we? So those people that are having their heat pump blowing cold air, it's not blowing cold air, it's blowing 98-degree air, but it's moving too fast. Too fast! How cool is that? You following? Absolutely. Absolutely. Cool. Okay. With the constant blower design, larger ducts equal higher CFM and lower velocity, lower speed. Smaller ducts equal lower CFM and higher speed. Does that make sense? I mean, that pretty much says it all, doesn't it?
Yes, sir.
Cool. So if I'm trying to get more CFM and I change the duct and leave the grill or the collar on that box, what's going to happen to the speed of that air coming through there? I've got this much air coming through there now, and I've got this much of a hole right there at the end. Wouldn't it be just like you taking a water hose and putting your thumb on the end of it? What happens to the velocity at that point?
Speeds up.
Speeds up. What happened to the quantity of air when I did that?
Shrunk.
Good, so you're seeing it. We might have a lot more flow through here, but here's where we choked it. Cool? All right. All right, high velocity issues. High velocity in the heating mode can give us that cold blowing air that we talked about. ECM motors with undersized ductwork create noise problems. Old PSC motors, the old motors that we were dealing with for 100 years, would blow against so much static, and then they would just say, okay, I can't give you that CFM. And they ran like that forever. The newer ECM motors, they're going to give you more air. But when they're going to give you more air through the same smaller ductwork, what do we know about the speed of that air? It's going to be screaming out of there, is that right? That might be a problem for a couple of reasons. Listen to air moving through a big duct. Listen to air moving through a small duct. What are they having to do every time the air conditioner comes on with small ductwork? Crank up that television, is that right? Up and down and up and down and up and down. You seeing what we're talking about? What's killing the motor? We hadn't even gotten there yet. Haven't even gotten there yet. We're just talking about the problems that customer is going to hear right off the bat. Yes? Cool. Filter grills. They're designed to stop particles at about 300 feet per minute. Well, let's stop and think about that. We talked about these filter grills, and we've told you guys in the past that you got to go with bigger and bigger filter grills. The old style we used to do can't work anymore. So what we're doing is saying that they're undersized. Well, if I undersize it, what happens to the speed? Good, okay, so it goes up. If a filter grill is rated to catch something at 300 feet per minute, okay, it's designed to catch it at 300. And if I make it too small, the air is going to be moving faster, is that right? So hold this filter up. You hold that filter, and that filter is designed to stop this egg at 300 feet per minute. Right? And if I throw it at 300 feet per minute, it does just fine, right? It catches it. But if you undersize it, what's happening to the speed now?
Hey, hold the filter.
What's happened to the speed if you undersize it a little bit?
It's gonna go faster.
That's going fast.
Going faster. So now it goes to 500 to 600 feet per minute. What happens now?
Busts you in your face.
The yoke's on you. The yoke's on you. Yeah, you see what we're talking about. And so if it goes right through that filter, where's it going to now? The evaporator coil, the blower motor, all that stuff, right? So now it's getting stuck on there. The filter never even caught it. Okay. So we have to size our filter grills at 300 feet per minute. I'm not sizing the grill per se, because I can get the grill to move air at 500 feet per minute. I'm sizing the grill because I'm putting a 1-inch filter in there. You follow that? Cool. So velocities also creates water blow-off problems. Remember I told you we're going to take this much air and we're going to move it through that 16-inch duct? What do you think is going to happen to the speed of that air when it's moving through that 16-inch duct when I got to move this much air every minute? What's going to happen to the speed of it?
It's gonna go super fast.
Super fast. What's the first thing that air sees when it leaves the return air duct going into that unit? Evaporator coil? Good. So it sees that evaporator coil going about this fast. What do you think it's going to do when it hits that evaporator coil going that fast?
It's gonna take all the water off of it and slap it everywhere else.
What? Water's going to be pulled off of that evaporator coil into that air handler. You guys haven't seen any problems like that, have you?
Absolutely not.
What if instead of, if I'm having to get it down, and it's kind of marginal because you're doing some marginal work out there because you're doing new construction. You have to keep the margins down. You can't just go throw big ducts everywhere, right? What if instead of coming in the back of that air handler with this high speed velocity, maybe I make that plenum just a little longer on the back and I come in at a 90 off the back, where now that air has to come in like this. Do you think going from this duct to this big square duct, what's going to happen to the speed if it goes from this to this?
It's gonna slow down.
Good, it's going to slow down. And it's going to take a 90, is that right? What's that going to do?
Slow it down.
Slow it down even more. So what if I go ahead and slow it all down before it reaches that evaporator coil? Do you think I have a better chance of keeping that water on that coil? Bingo. Cool. All right.
So Rick, when you speed that air going through that evaporator coil, what does that do to your heat transfer and your dehumidification?
Well, this warm air is going to go across that evaporator coil. I don't have a lot of heat because we slowed down the amount of quantity, right? So I've got a small amount moving very fast. Let's call that 35 degrees and this 80 degrees. If I was going through there at that 350 feet per minute, I'm going to go across that coil like this. Oh, it's going to cool me down, and I'm going to go right on through. Is that right? If I undersize that return air duct, and now that air is going, what? Oh yeah, you got it. It's going across that coil like that now. How much time was it able to stay in? It didn't have any time, did it? If I didn't have any time to lower the temperature, do you think it stayed in contact with that coil long enough for it to be able to start to condense? If it didn't have any time to stay in. So what happened to dehumidification?
Gone.
What happened to the cooling?
Gone.
You seeing this?
What about y'all superheat? What does it do?
Drops it.
It does.
Yeah, that's what it.
If I'm not picking up the heat from the house, what makes that refrigerant super hot?
The warm air passing across
Heat
the walls.
transfer.
The heat from the house makes it boil. Makes it a boil because it's evaporating. So if I can't get the heat from the house to go into that refrigerant,
Then the
refrigerant didn't ever boil. It stays as a liquid. If it stays as a liquid refrigerant's a great cleaner. It's an excellent cleaner. What do you think it's going to clean out of the bottom of that compressor? All the oil?
Yeah, all the
Yeah. Or we might get liquid going. Can I compress liquid? No, we call that pneumatics. Oh, we can. Yeah. It takes about, what, 7 seconds, Mike? Is that what you said? About 7 seconds for you guys to take that liquid refrigerant and destroy a compressor. I heard it go pow, and then it just, my pressure's equalized.
Yeah.
Sounds like rocks in there. Oh, there's the rocks.
There's the gravel.
You know where your rocks are now?
That's debatable.
So say I go on a call and they have a unit that's, I mean, I'm not gonna say it's very old,
Okay.
but it looks old.
Okay.
When I open it up and it has, like on your blower and all your wires and everything, all the little furry things. That could be a sign of
How cold is that coil now because you got no heat?
Very cold.
Okay, if that coil is really, really cold because you're not putting any heat on it, that's where all the fungi starts growing, is that right?
Yeah.
So it starts growing inside
So
there.
that's actually a sign of
High moisture.
high moisture, but not the correct ductwork.
Low
or
airflow.
size.
Low airflow.
Yeah.
Yeah. God, we're gonna have to be able.
In the cabinet.
Yeah, or something adequate, yeah. But if you figured out that, hey, like I ain't got no leaks or anything like that, but
Yeah,
that would be the next option.
you know, I was just talking to somebody earlier today. I was just saying, you know, the Reed Marood, we put these nice little covers over the breakers, right?
Yeah.
To stop that moisture from going in there. And then we put a grommet about this big to run the wire through, and nobody ever seals that. So we're gonna take all that air and go right through there. So didn't really do a lot except protect the front of the breaker, right?
Yeah.
That's gotta be sealed.
I got you.
Cool? All right, but that's a completely different problem.
Yeah.
Good,
Yeah.
all right, good, all right.
I remember in the old days when they used to take a roll of permit stuff and seal all those little penetrations on there.
You can't remember old days.
But that took like 10 minutes every carry time. Oh, God. Find some on our shelves. I tried to.
All right, so total pressure, guys. Remember we talked about the velocity pressure right down the middle. It likes to be there, it doesn't like to turn. Static pressure is all directions. Total pressure is the combination of static pressure and velocity pressure. Somewhere between nice to know and who gives a damn, because we never measure that. We're primarily focused on the static pressure on our systems. The velocity pressure we need to know about because that comes into play every time that duct does this. Every time it does this, it hits that wall, then it hits this wall, then it hits this wall, and the static pressure increases because the velocity pressure increased. Does everybody get it? Cool. All right.
What have we learned about Brady? Y'all thinking Brady is a psychopath about these ducts being straight? Brady is not a psychopath because he just wants the air to stop hitting walls every time it does this.
And he doesn't want to buy 25 feet of flex to run 10.
So can I convert static pressure into velocity pressure? I think we can, because let's stop and think about this. If I have a balloon and it's pinched off, what kind of pressure do I have inside that balloon? Static. Somebody said air pressure one time. I said, yeah, asshole. Static pressure. It's pressure. It's pressure in all directions. Is that right?
Yeah.
Good. All right. So what do I have in a plenum that's sealed off? What kind of pressure do I have in there? It's all sealed up. Static pressure. What if I tied a branch duct onto this plenum? Did I convert the static into velocity? Good.
Yeah.
What if I tied a branch duct onto the side of this plenum? Would I convert the static that is on the sides into velocity?
Yes.
Yes.
Good. How important is static pressure in order for us to be able to get air out of a branch duct?
How else are you going to get it out?
Good, because you're going to find the idiot, and I was an idiot too. I know Dave was an idiot too. At some point in time, somebody is going to tie a duct onto the end of that plenum. And when you did it, am I going to get air out of the end of that duct?
Damn right you would.
What kind of pressure?
All of it.
Velocity pressure, right? What happened to my static pressure when I cut that hole at the end of that plenum?
Rock.
Static pressure went down, so what happened to my...
It went down.
Good, see what happens
Everything
here?
went down.
You see what happens? I have to have the proper amount of static pressure in order for the duct system to work properly. If I don't have enough static, it's not coming out. It's just going to find a path of least resistance and go there.
But it always wants to go straight, it never wants to turn.
So are you
it's
suggesting
straight out.
the first 12 inches and the last 12 inches of that plenum are off limits?
Yes.
I think I will suggest that, but yes, if you want to suggest it now, I'm good with
That's
that.
normally what you do on a regular plenum straight off your unit anyway. You want to leave about a foot off of there, then start.
Good.
Off-
Because how fast is it coming,
Yeah.
how fast is it coming out right out of that plenum?
That's fast.
About 700 to 900 feet per minute. And you tie that first 12 inches, how quick is it gonna make that 360 or that 180? It can't do it. It can't do it.
How much can the damper direction on that duct actually affect your airflow?
It can. Usually more when your velocity is in control. And I'll cover that here in a minute as well. Good calls.
I mean, everybody's got their own idea. But how much does it actually affect?
It depends on how much velocity is really taking place, and I've seen a whole entire duct system change where the whole customer is completely satisfied when I just rotated the damper
Oh,
90
yeah,
degrees.
yeah.
I've seen it done, yeah.
Yeah, so now everything's great. Before, oh, I hated it, but just rotating it 90 degrees,
But I mean,
everything.
is it normally the way your airflow goes, that's the way you put your damper, right?
And I'll cover that, absolutely, it will.
But like if your airflow, say it's an upflow, you would put your
Damper.
damper going that way.
Good.
But why wouldn't it be better to do like this so that damper could catch?
Oh,
Is
okay.
it stopping or
Okay,
slowing you
so we're
down?
gonna scoop it, right?
Yeah.
Yeah.
Yeah, that's a scoop it system. If it scoops it, how much of the duct am I using if I'm scooping it?
Oh, right.
How much if I have static,
Yeah.
how much of the duct am I using now?
Yeah, the whole thing. Yeah, I got you.
It's little things like that. And once you get it, you'll never forget
That's
it.
what I'm saying.
Absolutely.
I thought about it, yeah.
It's amazing to me that you can ask 10 different people that question that have been in this business for decades and you're gonna get 5 different answers.
Good, I hope I gave the right one.
And I normally,
I thought the one you gave was supposed to be the right one.
we normally,
That's what I thought.
all do that too, wherever the airflow is.
My guys did, the wing nut was on the top and the wing nut was on the right side.
Yeah.
That way, anytime my guys went back on a call, they knew where the
Yeah, on
adjustment
your right
was.
side or on top, yeah.
You didn't have to start cutting the whole duct, trying to figure out where it was all at. It was right there. All right, so air movement through the duct system. It starts here. This is your lungs. It blows across here, blows across the heat exchanger, blows across the coil. Is the coil resistance to airflow?
Absolutely.
Yes,
Yes, there's some resistance there in there. Okay, what about the ductwork? Is that resistance to airflow?
yes,
Sure. What about the branch ducts?
yes.
Good. What about the grills?
Yeah.
Yes.
Good. So then it moves into here. So even in my whole system, this is really ductwork, isn't it? Because I'm converting air from one place to the other. So it gets it all the way over to here. Then it comes into the return air grill. Do you think that's got some resistance?
Yes.
Good. Ductwork itself, resistance?
Yes.
What about the filter? Resistance? Yep, absolutely. So we have resistances all along the supply side, and we have resistances on the return side. That manufacturer of that blower said, if you give me this much resistance, I'll give you this much airflow. You are in charge of the resistances. Does that make sense? Cool. All right. If the air distribution process is undersized, closed off, restricted, the entire system is disrupted. Disrupted airflow can cause compressor flooding, noisy systems, dust. Yeah, dust. We can have a lot of dust if I start having that air become very, very dry because of the heater overheating. Drafty rooms. What if I had a room that just had a very small duct on it during the winter time, and it was, don't you think that you would feel that air moving around? What would air feel like on you if it was moving around during the winter time?
Cold.
Drafty, yes, drafty, absolutely. There's the drafty room. Mold, mildew, could that happen if I had problems with airflow? Sure. Electrical problems? Huh. Let me ask you this. That fuzzy unit you talked about. When you got into the electrical panel inside there, what did you see? A lot of water?
Moisture, yeah.
Okay. How's that moisture work with that electricity?
Not
Rusty.
Oh, okay. Rusty breakers? What? Yeah, okay. So could I have electrical problems based off of airflow?
Yes.
Absolutely you can. But if you only fix the electrical problem, you never fix the airflow problem, are you going to be back?
Yeah, you're gonna right back.
Absolutely. Motor wear?
Yes.
If that motor's trying to get that air through there, the bearings are going to wear out.
Yep.
Positive or negative pressures in the home. We'll talk about that a lot more. Heat exchanger failure? Yep. Because it's not moving the air across it, that heat exchanger is going to get hot.
Right.
Good. Humidity problems? Absolutely. Sweating ductwork?
Yes.
Yes, absolutely. That's all of the things we're going to talk about, and you've seen it. All right? The blower delivers the air to specific static pressure to the ductwork. It also returns that same amount of air. Whatever it shoots out, you're supposed to have coming back. The blower design dictates the CFM and can deliver that given static pressure. As the blower operates against a lower static pressure, less resistance, it can give you more air. If it operates against a higher static pressure, it's going to give you less CFM. So, PSC motors, constant torque motors, and constant airflow motors. These are the newer ones. This is one you primarily see, but this is that true variable speed motor, right? This is what we've dealt with for the last 45 years. So, if I can give you an idea what it looks like, as the static increases, this is what happens with the blower design. It doesn't deliver that CFM. So as the static increases, CFM decreases. Okay. A constant torque motor. It's more efficient. It can do better than a static, an old PSC motor. It will do better, but again, as the static increases, the CFM is going to decrease. It'll do better. So now what you have is that undersized ductwork that you pull the old PSC motor out. You're going to get more air through that small duct. What's it going to sound like? More air through a small duct. It's going to be noisier, right?
It's like more air going through a small duct.
It sounds like more air going through a small duct. That's exactly right. So we need to pay attention to that, because as we're starting to put these new ones in on the older duct systems, the customer's going to complain that it's noisy, yes? If they complain it's noisy, tell me what you're going to do when you go over there.
Check the duct.
Oh yeah, come on. What would you do if she told you it's blowing, it's loud when it comes on? What are you going to do?
Move some air.
Move some air.
Yeah.
You're gonna take the tap on that motor
And move it from high to low.
You're gonna go from high to low.
So we went from not getting enough air to lowering the fan speed on there and not getting a lot more air, right? You guys are getting this, right? We can't afford, if I slow that amount of heat down across that evaporator, it's going to cause that evaporator to get colder, and we're going to get liquid going back to my compressor, and I'm going to get a bunch of busted scrolls. Cool? All right.
And everyone in this room will live to see the day that the PSC motor goes away.
Yeah, this is well on its way out.
It's almost
2-3 years.
Yeah, if it goes that long.
I don't know that there's going to be any air handlers with them left on our new equipment line.
Well, gas furnaces are gone.
Those have been gone, but
Yeah.
on the new lineup of equipment that's coming out in 2023 in Rude,
I'm sure there's going to be still one, because there's going to be one that we have to.
114.3 steer straight cool
Yeah,
system that we're going to have.
I think most of the condensers they'll be going on.
We probably won't stock it.
No. Now, the downfall to that is that we're going to see all these ECM motors and the condensers, and they don't fail because of static. They're just junk.
Well, they were junk, and I'll give you that. And they knew that they were junk. And what was the date, Jody? That was almost what? 2020. 2020.
They're still popping up.
I just need serial numbers.
I need some numbers.
And I've asked you for the serial numbers in the past. We need them.
I
Got it.
Can't do anything.
I can't fix it if I can't prove it's broke. All right, constant airflow motors. These are the true variable speed motors, okay? True variable speed motors. What's gonna happen to its airflow when I have static increase? It's gonna stay. It's gonna stay doing the same thing. It's gonna get you that CFM because that's what it's designed to do. You increase that static and it's gonna get you that airflow, or it's gonna die trying. As soon as you get that static pressure up in that 0.8, 0.9 range, right? I'm gonna smoke that motor. And where were we hanging around, Hunter? 1.2, 1.4.
On the Ford Sun, I think it was 1 point something.
Okay, so we know we have these kind of issues. And we have it across our footprint. It is not just here. But what I need you guys to do is start measuring it so you identify the problems. Fair? Cool. All right. All right. So, feet per minute through the duct system. Guys, without being able to tell you how fast the air should be going, it's just kind of a moot point saying it's moving too fast, moving too slow. So if you have metal duct, this is typically the numbers that you would be looking for. Metal duct, supply trunk, 700 to 900 feet per minute. In the supply branch duct, it drops down to somewhere to 600 to 900. Supply grills, 500 to 700 coming out of there. 500 if I don't want to hear it. 700 is like commercial where you start hearing some of that air moving. So somewhere in there, but residential you typically want to go closer to this 500 feet per minute. Terminal velocity is 50 feet per minute. So if the air comes out of a grill, across that room, it's going 500 feet per minute, right? Out of that supply grill. 500, 400, 300, 50 feet per minute. If it's cold air, it's going to start to fall. If it's warm air, it's going to start to rise. Terminal velocity is where it quits going in the direction you wanted it to go and it starts reacting to thermodynamics, okay? It's going to either rise up or fall down. Terminal velocity. Filter grills. I want that air at 300 feet per minute through a filter grill because of the filter, is that right? Good. A return air grill with no filter in it at all, somewhere around 500, because I can get air through the filter grill, but I can't move it fast because of the filter. The grill itself, I can move it through. Am I going to hear it at 500 feet per minute?
Come on, guys, a question.
500 feet per minute is that quiet. That's that quiet piece, right? I don't want to hear it, so I'm going to get the air slow enough to be about 500 feet per minute. If I run the supply air at 500 feet per minute, I told you that's going to be that quiet air. So good. Return air grill, 500 feet per minute. Return air branch is somewhere about 400 to 600. Return air trunk, 600 to 700. If I'm worried about velocity across that evaporator coil, do I want to be looking at 600 or 700 feet per minute across that coil coming into the back of that? I want to go slower, right? The slower I can, so the bigger the duct, the slower the air.
Yeah.
The velocity. Still got the quantity of air, yes, because I got a huge area. But the speed slows down. Does that make sense?
Yeah.
Cool, all right, we're good. So, we talked about free area right there. And if I'm talking about a grill, I'm typically looking at 90%, even down as low as 50% of free area on a grill, which means some of those grills that you guys get, those stamped grills that are very tight, most of it is blocked up by the grill itself. So I might only have 50% free area on that 12 by 12. But if I'm getting a grill similar to these, where I've got a lot more free area, I might be closer to 90% of free area. Which way do you think it's going to have less resistance? Something with a lot of free area or something with a very little amount of free area?
Free area.
A lot of free area is going to be less resistance, is that right?
It's resistant because it can pass through.
Pass through, that's right. So which one do you think costs more? This type of a grill that you can get a lot of air through, or something that's just stamped and you don't get a lot of air through?
Ross, answer this one.
The cheap grills are going to have less air, is that right? But there's a reason they're cheap, yes?
Yes.
So we want to have some.
And the sad thing is, this area, this market, has always been the highest volume of the better grills, and that is diminishing by the day because the
Cost.
cost is just going through the roof. You know, that $100 grill is now almost $200.
Yeah.
Get it, understand.
We're seeing more and more stamp grills going on jobs from people who would never touch it.
So the whole reason I need you to understand why you would put on that type of a grill, because the customer doesn't know any difference. And they're just saying, oh, I want a cheap grill. So you're putting on a cheap
I
grill.
want a cheap job.
Yeah.
Yeah.
Good.
I want a first-class job, but
I don't want to pay for it.
a cheap job.
So the idea is for everything that these guys are talking about, he's just giving examples. He's giving you the whys. What our goal is to do is to get y'all to understand the whys to where y'all can explain to a customer the difference of, oh, well, you know, the three-way,
It's not just prettier.
that three-way grill is they're just more expensive because they're aluminum. No.
No, they're not.
No.
No.
More airflow.
More airflow. Yes, they're aluminum. Yes, no, they're not gonna rust. All this other stuff, like, it's better for your system as a whole.
Yeah.
So flip over the duct calculators to the back. On the upper right-hand corner, you see that CVA that I've got right there? Good, look right below that. See all those velocities I just ran through? Good, so I put it on there so you know what velocity should I be kind of seeing through the duct system. You say, okay, well I can work with that. And you say, well, what is this CVA? Well, this is CFM. This is velocity, that's the number you got right there, right? And this is area in square feet. Area in square feet. So if I have a 12 by 12 grill, how many square feet do I have on that? 1 square foot. Does that make sense?
Yes.
Good. So if I have 100 CFM going through 1 square foot, CFM divided by area gives me velocity. 300 CFM, 1 square foot is 300. So you're understanding that this CVA, I can find out the velocity, I can find out the area, I can find out the CFM. If I know the velocity in the area, velocity times area gives me CFM. How cool is that? CFM divided by the area gives me the speed. If the speed is too high, based on what you're supposed to have there, you know that, oh crap, my speed's too high, that's telling me my ductwork is too small. How cool is this? Is this good stuff? Good stuff, okay. Well, CFM, velocity, area in square feet. Everybody cool with that so far? All right, let's take a look at this. C divided by V equals A. C divided by A equals V, and V times A equals C. If you ever took any Ohm's law in electrical back in school, it's the same stuff. Okay? Amps, volts, watts, volt ohms. Good. So here's what we have, and let's play with it a little bit to kind of see what this really means. All right, so I have a 24 by 24 grill. Okay? 24 times 24 is 576 square inches. 12 by 12, 12 times 12 is 144 square inches per square foot, yes? Good, so if I have 576 square inches divided by 144, I can get 4 square feet. Does everybody follow that? But look at a 24 by 24 grill. 24 is 1, 2, 24, 24. That's 4 square feet, yes? Good, so we know that this is right. Cool, all right. So I've got 4 square feet of filter. Let's say that I want to put 300 feet per minute across that filter, right? Because that's the speed that we wanted to go. 300 times my 4 will get me 1200 CFM. So a 24 by 24 grill can handle about 3 tons of air. Does that make sense? Cool. Well, that's kind of cool. I can kind of work with that a little bit, yes? Good, let's kind of work with that a little bit. Let's see what happens. Here's another one over here for somebody else.
The height times the width times 2 things are much simpler.
Yeah, but so what I got to do is I got to figure out how can I make that's going to apply, but now I got to apply it to underneath that grill on that door. I got to apply this to what's going on inside the ductwork. Okay, so this is how commercial is set up.
I've seen them use that calculation.
Commercial is completely set up like this. Residential is based on static. This is based on velocity. So all commercial is set up with CVA. So let's take that and apply it and see how it works. So what happens when a guy says, I want to be able to move, 1600 CFM? Because there's a lot of people out there that say 1 square foot per ton. And you'll hear them say that. You need 1 square foot per ton, but let's see what happens there. 1600 CFM, now going through 4 square feet, 1600 divided by 4, what happened to my velocity?
No, it went up.
Way up.
It went to 400.
You got on this side of the grill.
You with me now? Huh?
Hold that little.
You're with me. You're getting it, right? What happens now? Because they said, oh, yeah, how fast is that egg coming now? Faster than the filter can catch it. Does that make sense?
Yes.
Cool. So that myth is blown. They can't use...
You ever hear the 144 square inches?
144 square inches per ton is 1 square foot per ton. 1 square foot per ton is what we just did here, and the air is moving faster than the filter can catch it.
Rick, show them what to do with the 144 or the 1 square foot per ton of this. Like this.
That's
Throw it in
it.
the trash. That's what y'all
Guys, we're all taught from the guy who learned from the guy who learned from the guy. We never do understand the physics behind it or anything like that. The first installation of air conditioner was an engineer with an engineer helper. Mr. Carrier had an engineer helper on his job. And then we've just slowly gotten worse and worse and worse until you got to the butt crack mechanic, me, that I knew that there was 4 parts inside that condenser, and if I changed 3 of them, I was going to get that thing to run. It's swinging back the other way. You guys have to be a lot smarter than we did as technicians back in the day. Cool? All right, so.
But you have so much better tools to work.
What about this 2000 CFM? If I put this 24 on a 5-ton unit, how fast would that air be moving now?
Real fast.
Somewhere about 500 feet per minute, is that right? Wow. Are you good? So you're getting it. What's going to happen? What's going to happen to the dust going to that filter?
Straight through.
Straight through.
It's going to go to the blower.
Good.
Blower.
Are you with me?
Stick to the wet coil.
Cool. I don't want you guys to, when somebody says, oh yeah, well you can do it because I've done it for 40 years. I don't want you to buy into that.
Yeah.
I need you to be smarter than that. So do you like this? Cool. All right, let's try it again. Let's see something. What if I had 500 CFM going into the master bedroom suite? Right? I've got a couple of ducts in the master bedroom. I got one in the master bath. I got one in the master closet. I got all that going into the suite, right? And where's the return?
Across the house.
Right? So what are they gonna do?
Close the door.
Close the door. And if I close the door, where is the return now?
Bottom of the door.
Good. And how much do I have to cut off?
Half the door.
1 inch, right? Because that's the standard. That's the standard in this industry.
But I don't ever close the door.
No.
I don't want to know that. You just have to be quiet back there, because I know you sailors back there. You guys are weird. All right, so that's how we have to do that. And 1 inch off the bottom is not going to do it. Let's prove that out. 1 inch by 36 inches. A 3-foot door, yes? That's 36 square inches, is that right? Divided by my 144, that's 0.25 square feet. Yes? Everybody okay with that?
Yeah.
500 divided by 0.25,
Calculators, guys.
They're in your phone.
2,000 feet per minute.
if I told you that air is moving 2,000 feet per minute underneath that door, and I told you the most you want coming out of that grill was what?
500.
500. What do you think it's going to sound like on the other?
It's gonna comb your hair.
If that dog walks past, if the cat walks past there, it's just going to be fluff going poof. Is it going to be able to get that much volume under that duct? You see what I'm saying? The resistance is going to be going through the roof. What's going to happen to the pressure inside this room?
Build up.
Build up.
Good. So every crack and crevice in this room right now, when that room goes, where's that air going?
Wherever it can.
There. You'll look at the light switches. You'll see it on the light switch. You look at the receptacles, you'll see it there. Can lights, I can get about 30 CFM through a can light. If I got all that air going out on this side of the house, it's going to be coming in on the other side through every crack and crevice. Does that make sense? Cool. All right, so not good, right?
What happens to your airflow out of your grill when your room pressure goes like that?
I don't know, let's see. Blow into a Coke bottle. What happened to the CFM when I blew into a static room?
Stop.
So if you do feel air coming out of there, and that door is closed, what air I feel coming out must be
Going out.
either going under that door or going through every crack and crevice. Does that make sense?
Yeah, I got you.
It's scary now, isn't it? Because now you know something. Yeah.
But my master bedroom's always hot.
Oh, really?
It's always hot.
Wonder why. Look. How much air are you getting in? You follow? Cool. So let's cut off 3 inches off the bottom of that door. Okay? Cut off 3 inches off the bottom of that door. 3 inches times 36 is 108 square inches. Divided by 144 is 0.75. Everybody okay with that? 500 CFM divided by 0.75 would be?
The devil's number.
The devil number, that's it. The devil number is 666, right? So with that 666, how fast is that air going underneath that door? Enough to make noise?
Yes.
So it's still noisy. You think that room is still being pressurized because it's trying to get underneath that door?
Yes.
I think it is. Can't do that very well. We cut off 3 inches off the bottom of that door. What are we gonna have to do now?
Looks like a mobile home everywhere.
Do it back. You're gonna have to do it back because that homeowner's gonna be.
We're gonna cut off 4 inches. We're gonna be right there at the hinge now, all right?
Okay.
You don't have to worry about privacy because the kids are going, hey, what y'all doing?
Like that.
You know, we're talking 4 inches off the bottom of that door, and that's a woman's 4 inches, not a man's 4 inches, all right? So we're talking about running that to there. 4 times 36 is 144, divided by 144 is 1 square foot, divided by 500. Now that air is moving under there at 500 feet per minute. Can I use cutting off 1 inch off of the bottom of that door as the return airs?
Absolutely not.
Do Do you have proof now?
But do we?
Absolutely. Of course.
But a 12 by 12 grill,
Go to a new house.
but a 12 by 12 grill right above that door would do.
I don't know. Will a 12 by 12? How much can I get through a 12 by 12?
300.
Mom, Dad, can y'all keep it down over there?
So a 12 by 12, we said
No.
that was
That's 144.
1 square foot, right?
Yes.
So if I have 500 divided by 1, right? 12 by 12, yes, 1 square foot. 500 divided by 1 is 500. How fast do I want that air moving across that grill? 300 on that grill, right? Yeah, so what's going to happen to that dust going through that filter grill? If it's moving 500 and it's only designed to catch it at 300,
Go straight through.
there it is. You with me?
Yes.
Good, 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 good. You like this? Huh? Fat Man gave you something good, right? Huh? There it is. Oh, what if I gave you a calculator that could do it? What? Okay, so on the Coburn's Connect app, we've got the square foot calculator.
How much it cost?
It's absolutely free, 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 free. So square foot calculator, if I put in the length and the width, it will give me the square foot equivalent. Is that good? Don't even have to break out the calculator, is that right? Everything's good in your world. If you put in a round duct size, it'll give you the square foot available as well. Is that good stuff? Good. You have it on your phone?
That was the first one.
Well, let me ask you, do your guys have it on their phone?
They do now.
Do not.
Good, good.
The one at the end actually listened at one time. And
Yeah, I did have an account, I just had to reset the password.
So everybody's good with this? You think this is good? Okay, well let's do the CVA calculator too. Because if I know the square feet, I can put that in right here. If I knew how much air I was blowing into that master bedroom, right? What's the velocity now? 2,000. So I did all the math for you guys. You don't have to start playing around with that. We built it right into. These guys work hard trying to make these calculators happen for y'all. Be kind of nice to use it, right?
Yeah.
Sweet. All right. Good stuff so far? Good. All right. Supply trunk, I told you is going to be somewhere around 700 to 900 feet per minute. Is that right? That's the speed of that air going through there. Look at the back of the duct calculator. Does it tell you on the supply trunk how fast the air is supposed to be moving? 700. Good. There you go. Right there, right? We're good. All right. Volume dampers. Oh, wait. Look at this. Volume dampers. Volume dampers are used to regulate the amount of air in the branch duct. They should be installed with the blade in the direction of the airflow. So what if you said air upflow unit, right? And you said it goes up and down, right? Unless I put a T. As soon as I put a T on that,
It just became horizontal.
Then you
the direction of the airflow.
yeah, because you're not gonna put a
Damper.
damper or anything on your T,
Right.
on the throat or anything.
Right.
You're gonna be changing your airflow.
Good. So my direction, whatever direction my air is flowing is the direction that I want to have the damper. Is everybody okay with that?
Yeah.
Cool. So again, if I had air coming up and I'm scooping it, how much of the duct am I actually using? Half of it. Absolutely. I might get air that I scooped out of it, but I still don't get near what I would have if I turned that this way and had static pressure.
So pretty much you're going from an 8-inch to
Rick,
a 6-inch.
those are dampers and not scoopers?
Nope. I don't believe in a scoop it system. What? Nope. A scoop it system is just trying to scoop the air and it doesn't ever work properly. Good? All right. If it's blowing that way, put it that way, all right? Supply branch ducts typically are going to be about 600 feet per minute. I want to start slowing that air down from that 700 to 900 feet per minute in that trunk. Now it's going to start slowing down a little bit in that branch duct. And what's it going to do at that grill? Slow down even more. Why do you think I have a 7-inch collar on a 10 by 10 box? What just happened to the speed of that air when I went with a 7-inch duct to a 10 by 10 box?
Load it.
I made the area bigger What happened to the speed when I made it bigger? So now I can get 500 feet per minute out of that grill. Does that make sense? Good. Tie an 8-inch duct onto an 8x8 can, and what's going to happen to the speed of that air? It's going to stay at that.
It becomes a jet diffuser.
It stays at 600 to 700 feet per minute. Does everybody see that?
Yes.
Okay, cool. Supply boot, guys, the bigger you can make that, the quieter they are. They don't throw as far, but if I have them on the exterior of the home, where's the return air? Where's the supply air? I don't care if you're in first stage, high stage, middle stage, that air is going to come out and it's going to cross the room. But if you put these grills on the inside and try and blow it to the outside wall, when it's on high, it's going to do what? When it's on low, it's going to do what? Perimeter duct system. We got to put it at the load. Does that make sense? Sweet Jesus. All right. Supply registers and diffusers, guys, we just want to have that air moving 500 to 700 feet per minute, and typically on a residential, I'm going to want to go closer to the 5 than the 7. All right. So, high velocity, primary air. If that air is coming out and it's at a high velocity, it's moving out of there quickly. The primary air is going to be what I'm throwing out here. Is that right? Mm-hmm. The secondary air is that air that kind of just starts moving because air is moving this way fast. And this air is going to kind of start moving. I can have about 200% secondary air movement based on the velocity of the primary air movement. So what does that secondary air feel like on a winter day? Drafty. That's why we have to get these ducts large enough on a heat pump not to make the whole house feel like it's drafty every time that blower comes on. Does that make sense? Cool. Throw. You want the air to be able to throw 2/3 to 3/4 of the room. So if I'm blowing air off of this wall, I want it to go 2/3 of the room before it reaches terminal velocity, or up to 3/4 of the room before it reaches terminal velocity. If I don't do that, what's going to happen is that air is going to come out of here. If the grill's too big, it's going to come out of here and it's going to fall down. How are you going to feel over here? If it's already fallen down below your, yeah, so it's going to start feeling stagnant. You can start, it stratifies the air here. So you'll see air that kind of just does this. If I throw it too fast, the grill's too small, boom, hits that wall.
It's never going to make it under the door.
It'll never make it under the door. You feel down here in the occupied zone, you feel like it just missed you. So you're just feeling uncomfortable here. Does that make sense? Cool. So we're going to try and figure out how far to throw it, how fast to throw it, and the quantity of air we want to throw. You never thought you had this much air stuff, did you?
Yeah, you got to figure all that?
Yes, we're going to figure all that.
No, if the bedroom's that big, you put an 8x8 or 7-inch duct.
Good stratified air in the middle of the room if I can throw it 2/3 to 3/4, yes? 2/3 to 3/4. I want to get it that way. That works well. If the duct is too large, the grill is too large, it won't ever throw it that far. It'll get cool, it'll fall down, and run this way. If it's undersized, it's going to scream right across the top and work its way back. Return air branch ducts. Return air, multiple grills are used. Return air branch ducts can go somewhere around 600 feet per minute. That's a good slow pace for that air to start working its way back to that grill. Return air trunk, usually 6 to 7. I like to keep it closer to the 600 range. Keep it moving slow. You get one chance to put return air stuff in. Make it big enough so it's slow. Can I have too much return? Because it's a blower. It was designed to blow. If I've got this much air available, it's just gonna take whatever it takes, right?
Yeah.
So you can't make the return too large. Okay. Return air grills. There's filtered and non-filtered. Non-filtered grills, we said 500 feet per minute. Filtered grills, about 300 feet per minute. And we're putting the filtered grill at 300 feet per minute only because the filter's in there. Is that right?
Yeah.
Good, all right. So, calculating a non-filtered grill, height times width times 3, moves the air at about 500 feet per minute. Was 500 feet per minute a good sound level for grills? Good. So non-filter grills, height times width times 3, moves at about 500 feet per minute. Filter grills, height times width times 2, moves at about 300 feet per minute. Is 300 feet per minute a good speed for the filter? Oh yeah, so
Yeah.
nice. Let's make it easy. Let's say a 24 by 24, let's call it a 20 by 20 because the math's easy. 20 times 20 is 400 times 3?
1,200.
1,200. So a 20 by 20 I can use for a 3-ton system, is that right?
If it's filtered in the attic.
If it's filtered up there. If I'm filtering it at the grill, 20 times 20 is?
400.
400 times 2 is?
800.
So I'm only good for 2 tons if I'm trying to get the air through that filter grill. Does that make sense?
Yes.
Sweet. You like this? Good. It's on the back of this, so I wrote it down for you. You have that. But what about a 24 by 24? Let's try that. You guys break out your calculators. 24 times 24 times 2. How much air can I get through a 24-24? Cool. I'm thinking about 1152.
Yeah.
Yeah, pert near. Yeah, pert near. Can't see it from my house. Yeah, it's all right.
So you're trying to tell me that you can only put a 3-ton unit on a 24 by 24?
I'm saying you're pushing a 3-ton unit on it on a 24-24. Is that what I'm saying?
Marginal.
Yeah? Okay, so let's try a 24 by 30. We use those on 5 tons all the time, right?
No. It does. Tell me we use it as a 5-ton so I can kill y'all.
20 by 30.
Think I should do it?
24 by 30? Come on, let's do a 24 by 30. How much? 1440. Wow, is that even enough for a 4-ton?
Yeah.
Nope.
Wow. Cool. What about a 24 by 36?
1728.
Yeah. Yeah, I already did. Yeah, I already did it.
Ross has those numbers memorized.
So can I put it on a 5-ton? Your 5 tons typically are going to be right at 1725 on the root product. So yes, this is a good for a 5-ton on a root product.
It would be better.
Most of our new construction, minus one contractor that we work for, we're filtering them all of the units.
Good. So that would be times 3.
It would be better, that
Yeah.
grill would be better with a filter on the unit.
Yeah, we've kind of moved over to that. Helps us on our maintenance side.
Good. Does that work for
Would it
you?
be times 3 then?
Huh?
What would it be times?
Good. So let's do a 24 by 24 times 3. What can I get through there?
1728.
Good. So I can put a 24-24 on a 5-ton if I'm filtering up there. Is that right? Good. But on a 5-ton unit, would I want to put a filter grill in the master bedroom? Why? Why would I want to put a filter grill or some sort of a grill in the master bedroom?
Because they're gonna close the door.
Yeah, the door's always gonna be closed, or the kids and.
Yeah.
That's where the heat load is at.
See, that's why I call it Christmas. You know, once a year you get to open package and, you know, everybody gets happy. See, so it's Santa Claus, right? So you try and give them that opportunity to live in their home. Good. What if they have teenage kids? Where do the kids go after school? And what do they do to the door? Good. So could I put a grill in there?
Yes.
Would a 12 by 12 work in a typical kid's room if I'm filtering up there at the
Yeah, sure.
height times width times 3, right? Does that make sense? Is that, everybody's following along with what we're trying to do there?
Y'all got a test in the morning.
And you know-
I ain't giving y'all one today while the information's hot.
You gotta sleep on this.
We all know.
So here's the deal. 1-inch filters, 300 feet per minute. Your filters at the units, typically height times width times 3 gets you about 500 feet per minute. Anything over 1 inch, they're rated differently. Okay, so they're designed to catch it at 500 feet per minute. Cool? All right. So, look at this. It says this MERV rating filter, this 16 MERV rated filter, it's designed for airflow at 800 to 1400. They rated it at 1400. The pressure drop on there is 0.29, which is crazy. But look at what it's rated at.
492 feet a minute.
Good. So all of your extended pleated filters, that 5-inch filter, they're rated at 500 feet per minute. With my CVA, 20 by 20 equals 400. That gives me a 2.77 square feet. If I'm trying to move 1400, see? 1400.
Calculators, boys.
If I'm moving that 1400 through that 20 by 20, yes? Let's try it again. There's my 20 by 20 and there's my 1400. What's the speed of that air?
504 feet per minute, Rick.
Bingo. So they're showing you that at this CFM, through this, we can get that air to move at 500 feet per minute. So we're going to rate it at that 497 per near. Good? Is that making sense?
Sure.
Cool. All right. So, wait! What if I gave you a calculator?
Mother.
Talk dirty to me. How much is that calculator costing you today?
Free.
One time. Good deal. Free. Good. Guys, look at this. On the calculator, I've got filter grill sizer 300 feet per minute. Right underneath it, I have non-filter grill sizer at 500 feet per minute. How cool is that? So if I do this and I put in a 24 by 36, it gives me the CFM. You don't even have to do the height times width times 2 because we did it for you. Like it?
Mm-hmm. Love it.
I know you do. I know you do. Right here. So here's the golden piece to this. How fast did we want air to be moving out of our supply air ducts?
I believe that was 500.
500 feet per minute. Well, isn't that what we want to have the airspeed going through a non-filter grill? Well, wait just a minute here. Maybe, just maybe, I can take the non-filter grill sizer at 500 feet per minute and it can be used for extended pleated filters or a rough estimate for a supply air grill. How cool. So now if I needed to size a supply air grill and I needed a rough estimate of whether it can move it or not, I can go ahead and plug in that filter grill, that grill size, because you walk into them all the time. It's a 12 by 37. How much air can I get through there? Well, at 500 feet per minute, you can get easy enough. I love it. I think you guys do too. So let's talk about the duct styles, duct system style. They have the extended plenum system, which basically says, I want to take it from that air handler and I just want to run it down there, okay? But they have two types of that. They have the non-reducing plenum and the reducing plenum. And you guys like to do reducing plenums, yes? We do that. When do I put the reducer in? Oh, no. Just sometime we're going to put a reducer in there, yes? So here's a non-reducing, and here's the problem with that. If I just ran this out, same size, all the way down, and I start taking air off of this down here, what's going to happen to the static pressure all the way down here on the end?
It's going to go down.
Good. What's going to happen to the velocity on this end? Good. So what's going to happen to the air coming out of here?
It's going to move.
Some, maybe, kind of, yeah. I have no pressure in there. I have no static pressure because it all went out here. No static on the side. If I don't have any static on the side, can I convert anything to velocity? The balloon needs to be blown up to be able to have the air coming out. You follow? Cool. So not a great way. It's cheap because it's one size. Don't have to think about anything, but it's lousy for airflow. All right. Reducing size. On your reducing, we should have a typical minimum of 16 inches on our transition. Where do I put the transition? Guys, I don't know. I don't want to have anything right next to that transition, and I don't want to have anything close after that transition. Because look, if that air is coming down here and it hits that transition, where's it going?
Yeah.
Is that static pressure or velocity pressure that just went out that side? Velocity. I don't want velocity going out anywhere, do I?
Yeah.
I want to turn that into static pressure first. Good. So just kind of keep an idea on these kind of numbers. So the numbers get goofy because when you look at ACA's Manual D, which is the duct sizing thing, it says, as a general rule, after the air has been removed by a branch duct, after 50% of the air that's been removed. ACA says after 50% of the velocity has been removed. Well, hell, I don't know what 50% of the velocity is until I started measuring it. But then I started figuring out if I have 1 square foot, velocity and CFM are exactly the same. One's directly proportional to the other one. So I turned it around and said that if you reduce 50% of the airflow, the CFM, that's when you're going to reduce. That's when you're going to transition. So you have 800 CFM. You have a 2-ton system. You move 200 CFM, 400 CFM. Is that half of 800? Good, you transition. Now you're going to size that to 400 CFM. 400 CFM goes out, I drop 200 CFM off. Is that 50%? Good, I'm going to transition. Does that make sense? That way I'm able to keep the static up, and I'm able to keep the velocity up. Everybody with me? Good. I'm always sizing this next piece to how much air I have left. Remember we went from that 16 to the 14 to the 12? And we got to the 12 and we had 6 ducts down there at the end off of this 12. We didn't have enough duct left for our branch ducts. Does that make sense? Cool. All right. All right. Never take it off of a transition. What do you think's happening right there when that air is trying to go like this and then you're going to start taking a duct off the side? Oh, it's crazy. It's just nuts. It's going to screw up your duct system. All right? Don't let the homeowner start putting in scoops because that becomes a scoop it system, right? Don't let them play that game. All right, this is that perimeter duct system I told you. This, if you guys are going to start getting into any type of variable speed, high stage, 2-speed, anything, you guys need to start considering perimeter duct systems. If that fan is going to drop down to 60% or 50% of its fan speed, what's going to happen to the throw across here? It drops down, and then all of that just starts falling down and going out. I've got to keep that velocity up. So perimeter duct systems are going to be best. It's always going to go from there to the return. Go from the load. If I tried to put it on this side, can I ever hit the load? So what's that heat load going to do?
Start down.
That heat load's going to come right on through that wall. I've got to keep that load cool. Does that make sense? Cool. Warm placement of ductwork. If you're in an air conditioning climate, high and high is typically best for returns and supply, because what I'm going to do is I'm going to take that air, I'm going to shoot it out, I'm going to try and get it towards the floor. When I get it towards the floor, the warm air is going to rise up, and I want to take the warm air off the ceiling. Is that right? I don't want to take the cool air off the floor. I want to take the warm air off the ceiling. So if I can get rid of that warm air, that cool air will start stacking up to that 5 feet where we're trying to get everybody's face comfortable. Why do we put the thermostat at 5 feet? Because that's the average height of the face. And that's, the face is where we, so if you had a customer in a wheelchair, we're not dropping it down so that they can feel easy to work on it. We're dropping it down so that they can feel the comfort level at a space that they are. Does that make sense? Cool. All right. So if I had a warm climate, a cold climate where I'm doing heating, I'm going to go low and low. So I'm going to throw the heat up to the top, and what am I going to take off of the floor? All that cold air off the floor. Good. And that way I can warm the building up and have it come down to the face level. Cool. So let's look at these grills. What, you know, we talked about the grills and we talked about, hey, they're gonna do this, they're gonna do that. Let's find out what they can really do. These are both, I don't know, they look like both 6 by 12, 6 by 10 grills. Which one is gonna be best for what we're trying to do if it's a side wall? Well, if I have a room and I need 190 CFM in there, in this particular room, and the room is 20 feet wide, I'm gonna have to throw that air 20 feet, right? Or no, I don't throw it 20 feet, I throw it
16, somewhere around.
15 to 17, 2/3 to 3/4, right? Okay, and it's a sidewall grill. So let's look at the deal. To size the grill, you'll need to know the CFM, okay, that's what we have. Typical pressure drop, okay, we'll figure that out. We want less resistance, yes, good. The throw, how far I want to throw it, and I know I have the room. And how fast do I want to throw it? What's the speed that we're trying to achieve? 500, yeah, absolutely. So typically, if I get a good grill, you're going to see about 0.02 to 0.03 across that grill. If it's a stamped grill, what do you think it's going to be? Closer to 0.4, 0.5? 0.04, 0.05? Yes. When I get to these better grills, I'm going to be looking at that 0.02, 0.03. Okay, so that's going to be good numbers for us because that's going to decrease our static pressure total. The throw, 13 to 15 feet, right? Off of our 20-foot room. Velocity, we want somewhere 500 to 700. So this is a grill data sheet. When you guys are going to talk to Dave and say, hey, I need a grill that's going to fit this, he's going to open up his grill data sheet, or you guys can too, because you have an app. You also have GFJI or something. JFGI, just frickin' Google it, yes? So you guys have all of this information at your fingertips.
GTS, Google that shit.
Google that shit, all right? So here we go. Let's look at it, and we said, okay, let's look at this, and maybe we want to put a, I don't know, 200 CFM, because that was that 190 we needed to move through there, yes? 200, so that's the CFM. Let's put a size. Let's try a 12 by 6. When I look at that, 200 CFM through that 12 by 6, my static pressure is 0.037. And we said we wanted to be 0.02 to 0.03. Is that right? So this is probably a little more resistance than what we'd like to see. Is that right? Okay, well, let's look at this. It says the throw through A and B. A is going to be the big section, and B is going to be those smaller sections right there. So the throw is going to go 16 feet this way and 5 feet this way. We had 20-foot room, and we wanted to keep that somewhere between what? 13 to 15, 13, 17. Okay, so we're kind of close right there, but again, we're still probably a little bit farther than we want to be. What's the speed, the velocity of this? It's coming out at...
It's too high.
What are you going to do on this grill? What are you going to hear on this grill? Yeah. So would this be the right grill for our application? Probably not. We're not going to use that. So let's try a 14 by 6. Let's see what that looks like. 0.027, how's that working out? Yeah, we wanted somewhere between 0.02 and 0.03 would be a great number for us to be working with. It's going to throw at 18 feet. That's almost 20 feet, right? I mean, we're really got our throw too far on this one. Is that right? Good. What about this 588?
It's a little high.
Little high. Maybe that doesn't work as good as we want to have, right? So maybe this particular grill is not the one we want to have. Let's try that other grill. Oh, I know what I wanted to do. I'm sorry. Back up here. See this area, AK? That AK is the free area of that grill. That's 12 by 12, so that's 1 square foot, right? But the AK tells me that of that 12 by 6 grill that we were just looking at here, 2.9, half of the grill, half of 1 square foot is 0.5, right? Because 12 by 6 is a half a square foot. If I use all of it, that would be 0.5, but I'm getting 0.29 on the free area on that grill, right? Good, so that's telling me how much free area I have on that grill. We're going to use this 0.29. 0.29, 690, 200 CFM. If I know the velocity and I know the area, can I get you CFM? I had to use what? CVA. Watch this. 200, 0.29, there's your velocity. So this calculator is now showing you what's going to happen on that grill. If I know what the free area of that grill really is, I can tell you the exact velocity that's going to be coming out of that grill. Does that make sense? Mm-hmm. Cool? Good. All right. Let's try that other grill. That other grill we saw said, well, maybe this will work better. We know we needed to move 200 CFM. We know that we're going to try somewhere around that 12 by 6, okay? Let's try that one, 12 by 6. How about 0.028? We wanted 0.02 to 0.03, is that right? How are we doing? Good. Good? 14 feet, yes, the throw? Good. Good too, right? Good. The speed is 571. We wanted 5 to 700, is that right? Yeah. Good. Are we okay?
Closer to 5, so we're good.
Good. Yeah. So would this be a good choice for us?
Yes.
Much better than what we had on the other grills. Is that right? Yeah. Sweet.
There's a difference in the free area.
What?
Wow.
Watch what happens. 0.35, 571 speed, 200 CFM. Plug it right back in here. 200 CFM, 0.35, 571. It's screaming at you, this math works. The calculators work and they can work for you. Just use them. Cool? Where's the best place to start using these formulas? How about your house? Because once you start fooling around at your house, you go, oh shit, I screwed that, I gotta get that. Right? Cool. All right. All right, so let's take a quick break, and then I'll get you guys back in here, and then we'll get into some ductwork size. Fair enough?
Hey,
all right, listen, quick break.
I got some cold bottled water and ice chest in the back of my truck, but it's a freaking Yeti, and I'm not carrying it too heavy. Get your own.
Quick break. Get over there, get back.
All right, but I won't get long. Go over there.
Sometimes they use that sweet, that sweet.
Yeah, the sweet. No, but they use the sweet
Sweet onion.
onions too. That's what Angel does. They use the sweet onions.
All right, I got Big Mike back in here now, so we're gonna go ahead and get cranked back up again. Gentlemen, thank you all very much for keeping it short, sweet, and let's keep rolling. And look, you gotta jump up there and go grab you another sandwich. Go grab you another sandwich, okay? Nobody's gonna lose any sleep, okay? All right, here we go. Duct work. Oh, I don't like this kind of duct. Oh, I don't like this kind of duct. Oh, this one's crappy. Oh, I don't like this. This is good, this is bad duct. They're all good duct. How they're installed is where they become bad ductwork. Yes. So, you know, we have duct board. We have fabric duct. We have flex duct. We have metal duct. All of them are good duct. You say, oh, I hate duct board. I hate duct board. This is a 30-year-old duct system. That's not a bad age for ductwork. But if it's installed properly, it'll last.
I've seen many good-looking duct boards.
You have to install it properly. So, you know, you get the guys that say, oh, I hate flex duct. Flex duct gets a bad rap because it's not installed properly. If I'm doing this, talk to me, honey. If I'm doing this, it just doesn't fly, does it? No, we've seen this already. What's the velocity doing when I'm doing this?
Slowing down.
Good. So that velocity is getting, the velocity pressure is getting higher, which means the CFM is going down. Does that make sense? Good. All right. So lots of different types of ductwork. All joints should be mechanically connected and properly sealed. That means every joint, whether it's longitudinal or transverse or longitudinal when it goes down the length of the duct. Duct system is the delivery system of the air. It can be compared to your respiratory system, your breathing. Critical part of the system, yet it's industry ignored. We just say it's blowing air because this is what we've been using to check airflow for the last 40 years. That doesn't get it. We need to take the time when we're at home and look at the ductwork in terms of proper sizing, leakage, cleanliness, and overall condition. It's important to educate your customer about their duct system long before that they ever have to start replacing it. Because otherwise they're going to say, you guys have been doing the maintenance for the last 10 years and you never said anything that the ductwork needed to be addressed. Why would you want to drop a $10,000 bill on them when they don't have any clue that they've ever had any issues with their ductwork? Make sure that they understand it and prepare them for that going down the road. Fair? How would you got an extra 10 grand in y'all's pocket? I know I don't. Cool. All right. Ductwork is the conduit for air to move. It's important to seal the ductwork with mastic at every joint, both longitudinal across and transverse across the duct, along the duct or across the duct. While the ductwork doesn't heat and cool, it plays a major role in the efficiency. As efficiencies increase, the tolerances we had with the old duct systems are going to go away. We don't have that ability to be able to use improperly installed ductwork. It's just getting worse and worse. Proper insulation is a must as well. The state of Louisiana says that all we have to have is R6. The rest of the country is on an R8, which means that if the ductwork has less insulation on it, how fast is it going to see that 55 degree air go out to that 130 degree air if I only have this much insulation?
Fast.
Yes, if I have an R8, can I slow it down?
No time to get to it.
Yeah, so it's going to take longer. Yes, same thing with the moistures. Now, if it takes longer to get there, I have less chance of that ductwork sweating. Okay, so pay attention to that as we move forward. If you're going to be doing a lot of variable speed equipment, you want to start looking at R8 ductwork. Okay.
So why is it different in Louisiana than everybody else? How did we get by with that?
It was a lawyer in the state of Louisiana who didn't want to fur down one of his walls to get the ductwork in because you needed more room to fur down for R8 than R6. He said there's no reason to have that, so he wrote a law and ran it through the House and the Senate saying you don't need to have that, so why are we doing it? So the rest of the country is on R8 and we have to now change law if we're going. It's different from changing code. You have to actually physically write the law to change now.
So 49 other states are wrong and we're right?
Yeah, because we're in a wet environment down here. Yeah.
Well, originally it was to be all right.
Alabama and Georgia and Florida, they're not in wet environment at
That's
all?
what they kept telling us in the beginning when all that started. We're going after it, but you're all right.
Well, it actually became R8. It did, and then right after it became R8, which is whenever we adopt a code, we'd change that into law. And then he wrote a law saying that it only has to be R6. So now it doesn't matter what the code says, the law
So the
steps
code
over.
still says R8, but the law says 6.
Yes. So law is more powerful than code. Neat, huh? So,
Most of the sheet metal duct is still all full.
yes. So, which is why I like the M&M boxes. Duct board, rigid insulation board is 1, 1.5, 2-inch thicknesses. Can be fabricated on the job site quickly, it's very quiet. The flap joint must be stapled and sealed. We have to have a mechanical connection and a seal on there. Mastic all the joints, receives a bad rap because of poor install practices. Flex duct, externally lined with various R values, strapped every 4 foot horizontally. So if I'm going to strap it, it has to be strapped every 4 feet. You with me on that one, buddy? All right, we're just keeping you up to speed on that. I keep digging you because I know you're my man, right? All right. If I'm going vertical, it's going to have to be strapped every 6 feet. No more than a 1/2 inch sag per foot when running horizontal. Now wait a second, 1/2 inch sag per foot. I'm strapping it every 4 feet, yes? And I can only have a 1/2 inch sag. So between those two straps, I can only have 2 inches of sag total. 1/2 inch sag per foot over those 4 feet. So how close are we getting? Maybe? Yeah, maybe not. We got to stop that so that it doesn't keep doing this, right? Because that's causing that static pressure to go up. Cool? Usually one size larger than metal duct. Usually one size larger than metal duct to get the same amount of air through there. So if I'm using an 8-inch metal, I need to go with a 9-inch flex. Good? Okay. It's very quiet. If I'm going to put it together, I want to put the core first, pull the core up over the top of it. I need to then seal the core and then put a mechanical connection on there. So it's a seal and a mechanical connection. Then I'm going to go ahead and pull the vapor and the insulation up, and I do not need to put a mechanical connection on the insulation. All I need to do is have some sort of a seal on there, and I want to make it watertight. I don't want any moisture from that attic to go between that insulation and that core. Because if that moisture from the attic gets in between that insulation and that core is going to be 55 degrees. What's going to happen to that moisture?
Condensate.
Then that duct is going to be
Hang.
all pregged out, right? Cool. All right. Oh, like that. Not the way that we want to be running this stuff. Is that right? All right. We don't want to use paneling as an accepted duct design. It doesn't work. Just don't do it. And duct tape is not a mechanical connection and is not a proper seal. Unless it says UL 181 on the top of it, it's not a proper seal for the ductwork. Cool. Can it be a problem with me with codes? If I don't have a proper seal on that ductwork? Yeah, because we're building something not within code. And that follows you for the rest of your life. That's one of those things that just stays there for the life of that unit. Good? All right. All right, most mechanical codes require all transverse and longitudinal connection to have a mechanical connection and a UL 181 approved seal. Screws, Pittsburgh, staples, rivets, crimps, S and drive joints, those are all mechanical connections. And your UL 181 seals are your mastics, the tape, the pressure sensitive tape, the heat activated tapes, panduit straps, duct ties, that's all seals. So let's look at now some airflow through the T-fittings. What kind of pressure is this running straight up? Velocity. So I have the velocity running straight up to the top. When it hits the end of that, what's it going to do? It's going to have to go one or two directions. Is that right? Is that going to be a restriction right there? Sure. Yeah, because now it has to change directions. That velocity is going to have a hard time. Yes, it's going to stop it. So look at this 90 degree. Hunter, what happens on a 90 degree as it tries to make that corner? Where does all that air go?
Slows down.
Right? It's going all the way to the top up here. What happened to the amount of space I'm using when I have to go around that 90 degree? I just reduced the amount of space to half. Is that right? Wow, that's not good. So I've got a very high pressure build up here, and that 90 degree is making that just take up a little bit of space in that ductwork. I'm sure that resistance is starting to get very high right there. What if I did this? Look what happens now. Instead of having to make that hard right, I'm able to capillary around here. As it capillaries around, how much space do I have now to be using?
75.
Yeah, a good chunk of it, yes? Good, so what would be a better fitting, a 90 or a pair of 45?
45 would be better.
Yeah, you're seeing what we're trying to do here.
How beneficial are turning vanes? You don't see that anymore.
Turning vanes.
Oh, the vanes, yeah.
So what would happen if I had turning vanes in here, where
You would still have a little restriction.
what would happen to the air now?
Yeah, it would,
It would be turned.
the vanes would make it turn,
It'll help guide it, wouldn't it?
yes. But the 45,
So I'll say this to that. So David has a thing with, or we watched the film on this right here. And the difference between this and the 45s is twofold. One, it's really no difference as far as the airflow is, but the time and cost to do this versus the 45 is the difference.
yeah, I got you.
Good, but if this is already in place,
But yeah, if it's already in place, but say.
and I can add a few turning vanes in there to help, what's this gonna reduce? What is this gonna reduce? What?
Static?
Static pressure. If you're out on the job, you got 1.1, and this is gonna be something that's gonna help solve it. Is this gonna reduce the static?
Yeah.
Sure. Is it gonna get you down to where you need to be? Maybe, maybe not. Is it gonna help?
Yes.
Yes. Okay, a solution, yes? That's what we're looking for, solutions. That's what we're looking for, solutions. Very good. I like that. I'm glad you guys said turning vane in there. That worked out good. Good. What did they do? They used round elbows. So I need you to think about this, because this is why we switched a little bit. Round elbows seems like the right thing to do, right? Okay, so stop, let's think about this. The airflow through these L's, which one do you think has the best airflow characteristics?
I would say C. C, it's not D.
Or definitely maybe, right? What do you think?
I'm going to see.
You going C?
Yeah, I'm gonna go C with C.
Well, look, D is what we spent the money on. Yes? This is what we spent the money on. Because what does it do to the air? Yes?
It diverts the air.
That's what it does, right? That throat, it helps capillary it around that throat right there, yes? But wait, that's the throat here too. So we got the capillary here, yes? What do we have here? Here's what we've got here. Remember that little bit of air that we had that was kind of doing this NRT? Remember that? NRT, we had it like this, and that air had to go around here, and that air was just doing this right there? Yeah? Here's what's going to happen right here. That becomes static pressure right there. If that's static pressure right there, where's the velocity going to go?
Straight to the top.
Just like that. So, C and D are exactly the same. When it starts moving through there, you're going to have exactly the same characteristics moving through there, but which one costs more to make?
C.
I have to route this. That all has to be, this is way cheaper. So if you're going
Cut
to,
that round elbow by hand with a pair of snips.
Yeah.
and then you
You're not
have,
gonna cut it with a machine.
then you have to start bending in a 1/4-inch lip all the way through it so that you can put the Pittsburgh around the outside and drop that 1/4 in there. Try and bend a 1/4 on there. You're on there trying to run it through this machine. Yeah, okay, so which one costs more to make? This one. Which one is going to give you a better? Exactly the same. So if you're going to spend the money, don't spend the money on this throat, because this is going to have to do this, yes? Because that's where all that mess was here. Put the money in the throat, not in the heel. And don't worry about that. It'll come right on through. Does that help?
I got you.
Cool.
It's kind of like it's pushing the static
Yeah,
to,
just
to the corner and saying, stay right there, we're going through.
if a river was turning right here, what would you see right there in that edge of that river?
Wood, log, all kinds of stuff just swirling up right there.
And the water would be doing this, right? It's exactly the same thing. What is air? It's thin water. Yes? Because it does have moisture in it? Yeah, so it's just thin water. So whatever you think water would do in there, that's what your air is going to do. All right, well, that worked out pretty good. What about this? Give me a good, better, best.
Bottom one's your best.
Top left is good.
As long as they're going to the same room.
You should jump on the upright.
No, not even close, right? So then we're going to be bouncing off of the end of this. Then I got to change directions. Oh, the static, it's just going to get crazy. Avoid this as much as you can. All right, branch ducts. Branch ducts should not be tied onto the first
For 12 inches.
12 inches and nothing, definitely not off the last 12 inches. Is that right?
Yes.
What's the problem here?
That's too close to the cat. Yeah, too close to the cat.
Yeah, he took it right off the end of his trunk. Is that right? Am I working with static or velocity?
Velocity.
Strictly velocity, is that right?
Yeah.
Good. What do you think happened to all the static down here when he did this?
It dropped.
It's gone. That's right. So I can't get any air out of these ducts because everything's going on at this velocity. Is that right? Proper installation practices are a must.
Some beauty right there.
Yeah. Okay. The bitterness of poor quality remains in your mouth long after the sweetness of a great deal is gone. So let's talk about the ductwork leakage. Ductwork leakage is a good place to go, right? Let's talk about that. What happens when I have ductwork leakage? And we're not talking about a lot, because our ductwork doesn't leak, does it? Air leakage in the system can cause dirty, unconditioned air to enter the residence. It's estimated that every 1% loss in duct leakage in CFM equals 1% loss in capacity. Okay, so 1%, 1%, that works out. So therefore, if you have a 2.5 ton system and it only leaks 100 CFM, that 2.5 ton system just turned into a 2.25 ton system. But as you'll find out, it's worse than that, because as I leak that air out, I suck air in. And in Louisiana, it's hot and humid air. All right. Guys, if I have 1,000 CFM in, I want 1,000 CFM to come out into the house. I want the same amount of leaks in my duct system that I have in my refrigeration system. How much leakage do I want in that refrigeration line?
None.
Good, that's how much you want in your duct system. Let's find out what happens. If I have 25% duct leakage, in this particular case, I got an 800 CFM, that's 25%, 50%, 75%, 100%. If I have a 25% duct leakage here, 200 CFM goes into the attic space. That means 800 gets sucked out of the house, 600 gets blown back into the house. If I'm sucking out more than I'm putting in, that whole home just went into a negative pressure. If it's going into a negative pressure, I'm not just losing 200 CFM out here, I'm sucking in 200 CFM here. And in Louisiana, we said it's hot and humid. So I'm sucking in moist air in here. Your air conditioner doesn't do well trying to remove moisture. And the higher efficient we go, the worse it gets. So if I'm constantly sucking in moist air, your air conditioner is always trying to play catch up and it can't do it. Good? Supply air leaks is a problem. The home goes negative. But your guys are good air conditioning guys, so you're gonna put your meter in there, you can see that, oh, I've got a pressure problem. Well, maybe you're not gonna do this. Maybe you're gonna just take a piece of toilet paper and stick it in the window. And when you do this and you turn on that fan, if that toilet paper starts sucking in, you know that you got supply air duct leaks. That's kind of cool. If I got supply air duct leaks, that means I'm sucking in moisture into my house. Look at this, you've seen this all the time. It's just one little hole, one little hole. It's not a lot, it's just little holes. But every one of those little holes add up to a big hole. In this case, 8 square inches. 1/4 by 1/4, so 4 of these is 1 square inch. 1, 2, there's another square inch all the way around. I'm turning into 8 square inches all the way around there. I'll get back to you on this. If I have return air leaks, If I'm sucking 100 CFM from outside, that means I'm only going to take 700 from the house and blow 800 in. If I blow 800 in and only suck 700 out, the whole home just went positive. So every crack and crevice, I'm now blowing the green. Why do I have it green? Because that's money. Blowing bought and paid for air out of every crack and crevice of that house because of that. But now what am I sucking in from the attic space? Hot and humid.
Condensate.
Where do you think dust comes from? Remember we talked about dust?
Air conditioners make dust.
Yeah, they suck it in from outside. Or
Say that all the time, the air conditioner.
or if it's here, is it going to suck in dust from outside now? How about from every crack and crevice in that house? Because air is coming in, yes? Am I going to suck it in from around the cracks and crevices? No. Am I going to suck it in from the attic? Yes. If dust is coming in the house, it's usually because of duct leakage.
Yeah.
Does that make sense? Whether it's supply or return. Cool. So in this case, I hang that toilet paper in the window, I turn the fan on, what's going to happen now?
It's gonna blow out.
Good. So if it's blowing out, I know I have returned leaks. Cool?
If it's blowing out, you have,
The home just went positive, yes? If I'm inside the house and I put that toilet paper there, it's going to start going, yes?
yeah,
Okay. Cool. What is this?
mold,
Yeah, because of a return air leak. Yes?
hot and cold.
I sucked in all this moisture from the attic. This was supposed to be sealed right on top of that 2x. They were supposed to put a mechanical connection and a seal.
Yeah.
If they didn't put the seal, dust starts pulling in here.
You needed some silicone.
Every time that unit turns off, that moisture comes pulling in right into this cool area. If I've got moisture in a cool area, what's going to happen? Good. Let's make it even worse. Let's put in a really restrictive pleated filter and close that up. What's going to happen to the amount of air being pulled in there when it comes on?
More.
More. So much that it's even going to run around the filter on this right here. It was screaming at me where the problem was. The guy said, I can't get the moisture out of the house. Well, no, I guess not.
I got a question on that. Matter of fact, I went to the guy's house today again, and it just reminded me about it. On his return, whenever you put his filter in there, I swear to God, you could put it this far away from it.
So what does that tell you?
That it's sucking real hard, so it has a restriction on your ductwork. Your ductwork is too small.
If you had a straw and you were trying to get something out of that glass, could you do it with a small duct, or could you do it with a big duct?
Probably small.
Good. So if the duct is small, stuff's going to come up, just like you're talking about. That filter's going to go up if that ductwork is small.
Yes.
But if the ductwork is larger, I can get the air, but I'm not going to have the velocity. Is that right? You're telling me what's going on with that guy's return air grill?
Yeah.
What?
That the return is too small.
Absolutely it is. And it's going to hum.
Oh, yeah.
Why does it hum? Because it doesn't know the words. Bah! All right.
He set you up, dude.
He did.
Set you up, dude.
You just got the yolk in the face. The yolk's on you.
So guys, look, here's those returns that they tie right onto the back. What's going to be the speed of that going to that evaporator coil?
Well,
I've got this much space. Great. He kinked it off. He did a 90. He came right into the back. I've got this much space. What's going to be the speed of that air?
fast.
Good. What's going to be the quantity of air?
Lower.
Yeah, you seeing the difference. The speed is going to come in there. It's going to just knock that water right off of that coil.
And blow into your cabin.
Talk dirty to me.
Yep.
Yep, there it is. All right. See, it's not the unit, is it? It's not the unit.
Yeah.
It's our ductwork. We're screwing it up. It's us. All right. So proper S and drive joints, yes. What's wrong with this?
It's not sealed.
Good, I got a mechanical connection but no seal. Got to seal it. Don't ever use the building as a duct anymore. We used to be able to do it, don't do it anymore. It's not even allowed in the codes anymore. So look, if you put that collar on top of this sheetrock and you try and get, what are you going to get? I mean, are all those joists all sealed all the way down?
No,
you're going to suck dust and mold and dirt and everything all everywhere.
because it's going to pull from everywhere.
So if I've got return air leaks all over the place, the home's going to go positive. Does that make sense? Cool. Trying to avoid that kind of stuff. Look, this was a cable guy that went up there. He says, oh, it's hot. I'm going to pull this up. I'm going to cut this, so I'm going to end up with this. So now I can feel cool up there. If I have supply air leaks, what's going to happen to that home?
Negative pressure.
If I have it in negative pressure, what's going to happen to all that moisture that's outside?
It's
coming in. If I'm sucking moisture from outside, I don't care what kind of air conditioner, dehumidifier you guys are putting on there. If you're sucking it in fast enough, you got more water coming in your boat than you can bail out. Does that make sense?
Yes.
Cool. I don't have to tell you. You've seen it.
I've been there.
Yeah, we've all been there. We've all been there. And then, and we're going to go ahead and slap a brand new 20 SEER right on top of this puppy, right? Yes? And then you're going to call me and tell me that the equipment's bad? Look, I'm going to...
y'all sold me.
Yeah, y'all gave me that thing. Yeah, I know we did, because you gave me a check. But this ain't going to fly, right? It won't work. That's an asthma-ridden duct system that you guys are trying to put a new Jarvik mechanical heart in there. Not going to work. Remember that 8 square inches I just talked about on that collar? What is it really doing? What's it really doing? Let's see. CVA, I can use that because it's area, 8 square inches. Air moving through a supply branch duct moves about 600 feet per minute. We saw that on the back of the duct calculator, right? Good, so let's do 600 feet per minute. Let's do that 8 divided by 144, that's 0.056 square feet. Everybody good with that? Good, so 600 times 0.056 is
33.6.
33.6, okay, so I'm gonna go with 33.6, let's call it 34. So if I have a 2-ton system and has 6 ducts, and I'm moving 34 CFM on each one of those, 34 times 6, that's 204 CFM that's leaking out. Oh yeah, well see, now it makes, see that now it makes some sense. If I've got 204 leaking out of my 800, that's 25% duct loss. 25% duct loss, if I have 200 CFM going out, what does that mean about the house? I have 200 CFM coming in, yes? Hot, dirty, and humid air coming in. Does that make sense to you guys? So central returns. We talked about the one return outside. We talked about maybe putting something into the master bedroom so possibly we close the door, right? Exciting. If we can close that door, we can eliminate that room going positive because I've got a return air inside there. The problem is the rest of the country, they put a return in every room that has a supply. We, in our infinite wisdom, say we're going to put one return in the middle of the house and we're going to make it as small as we can get it. So the problem with that is I have to have every door open in order to be able to get the air going back there. Does that make sense? Let's see what happens when we don't do that. Here's the living room, the master bedroom, the kids' rooms, and there's the kids' bath right there. So the kids come home from school, they go into their bedrooms, and what do to the doors? They shut the doors. So if they're shutting the doors, we just eliminated all the return path. So now that air, whatever's coming into here, some of it's sneaking under the door, but the rest of it's going out. Is that right? If it's going out on this side, how much air does your air conditioner system make? How much air does your system make? How much air does your system make? How much air does your system make? It doesn't make any air, it just circulates air. So if I've got air leaking out on this side of the house, what does that tell me about this side of the house? If it's leaking out on this side,
It's positive.
it's sucking in air on here. Remember, every CFM that goes out, one CFM has to come in. Every CFM that comes in, one CFM has to go out. So if I just close this door and it pressurizes this room, CFM is going out. If it's going out on this side, what's happening on that side?
It's coming in. Yeah, it's coming in.
Yes.
Pulling it from there.
It's pulling from there. So this side of the house is positive, this side of the house is,
Negative.
and you go over and talk to that homeowner and you say, do y'all close the doors? And what do they say?
Never.
Oh, no, I never close the damn doors. No, I never close the doors. How are you guys going to be able to figure that out? You've got to be able to establish what's going on. Because right now, can they get the humidity level right in their home? What's it sucking in 24/7 that those kids have the doors closed? Yes, 100% humidity, yes. It's sucking in that humidity faster than the air conditioner could ever pull it out. So, remember that 1 inch off the bottom of the door? Look, real quick and easy before you have to break out your CVA, for every 1 inch you cut off the bottom of that door, you're going to move 4 CFM out of there. Look, Mike, I'm going to make it easy for you to remember. Look, Mike, 1, 2, 3, 4 CFM for every square inch. How you like that? Huh? You got that in your head? Yeah, Hunter goes, I'm glad he told him that.
No, he must have went to school in Monroe too.
So 4 CFM for every square inch. So if I have a 30-inch door and I cut off 1 inch, 1 times 30 is 30, times 4 CFM is 120 CFM. So if I cut off 1 inch off of the bottom of that door, and it's a 30-inch door, I can move 120 CFM under that door. But if I got 250 CFM in here, I'm going to have to cut off another inch off of the bottom of that door. Does that make sense? Mm-hmm. Real quick and easy, yes?
Yes.
Good stuff. All right. Well, we've got problems because we're sucking in air all over the place, and the homeowner said they don't close doors. Is that right? Good. Nice to know who gives a damn. All right, here's what we're going to see. You're going to start looking at light receptacles. You might pop off the cover. If you see a lot of dust in there, does dust grow or does dust collect? Collects. It collects because air is moving across it, yes? So if I see a lot of dust, that means I have a lot of negative or positive. Could it be going this way?
Oh, yeah.
Good, it could be. Yeah, it could be either way. I just know that something's happening there, yes? Good, so that's a good indication. If I see a lot of dust inside it, or it gets really grimy like this, that's telling you dust is going across it on a regular basis. Cool, you may even see it on the receptacle cover. If I'm seeing it like this on the receptacle cover, that's telling me it's gone negative.
Yeah.
It's sucking dust into the room. Murphy had a lot of it. A lot of it. Oh, my favorite, the door jamb. I never closed that door. Well, if I'm seeing dust in a door jamb, that means that door must have been closed. Is that right?
Yes.
Because now the air is going around it and getting, so my door frame is becoming my filter. Yes? So if you see dust in here, that's screaming at you that the door's being closed. If the door's being closed, we know that we've got pressurization problems, which means we're going to have moisture problems, yes? Sweet! So I'm going to pass my finger there, and I'm not going to say, look, lady, how dirty this is. I'm going to say, ooh, see, I'm seeing this dust here, which indicates to me that this door gets closed. Oh, yeah, we do close it, right? Now that the story's changing. Well, we do close it, but only at
Night.
Oh, yes. How long is night?
Half a day.
Half the day. Okay, so 12 hours. They've got this door closed, and we're sucking in moisture from the rest of the house, because this is positive, yes? That's all negative. We're sucking in moisture for half a day. How much moisture do you think I really brought in? A lot?
Yeah.
You guys don't have any moisture problems on any of your houses, do you? Liar, liar, liar. You just told me about one as we walked in here today. All right, good. So we're going to go checking these things. Jody and I are going out on one tomorrow for this same reason. Okay, we're going to have to investigate where the moisture is coming from. All right. So what can I do if I don't want to put? If the unit's way on that side of the house, and I don't want to run a duct from here all the way back there, could I just put a jump duct from the bedroom over the door into the hallway? Good, because then when they close that door and this room goes positive, where is all that air going to go?
Right back over.
Because the return is pulling this negative and the supply is pushing this positive. It's called a jump duct. It runs right back over to that side. Does that make sense? Easy, quick fix, does really, really well. Okay? All right. All right, so now, Jody, let's calculate CFM from external static pressure. We know that if the static pressure goes up, then that means that the CFM is going to go down. So let's calculate that. Let's actually measure that. Fair enough? Good. So this is a U-tube. I know. Us old guys invented YouTube long before you guys ever even thought about YouTube. This is a U-tube. It was just a clear plastic that went around here, and we filled it with water. And we filled it with water to the 0 level. So right here, I have no static pressure. But if I took a hose and hooked that hose onto here and stuck it into the supply air plenum, that supply air plenum, static, is going to push down on that U-tube water, yes? And this side's going to come up. So look, we have 0.1, 0.2, 0.3, 0.4 inches of water column. Water column, dog dirty, huh? We got 0.4 inches of water column on here. That's cool. So if I take that off, if I take that hose out of the supply plenum, what's that water going to do? Go right back to 0. What if I put one on here and stuck it into the return plenum? What is the return plenum going to be doing?
Something to be cooling.
Good. So if I plugged it into the return side, it might pull it up, how many? 0.1, 0.2 inches of water column. Is that right? I've got 2.2 inches of water column right there. You get crazy now. What if I stuck a hose from this one into the supply and this one into that return?
It'll equal out.
Will it equal out? Will that supply air still be pushing down on here?
Oh, yeah.
Will the return be sucking up on this side?
Yeah.
Well, if this one's pushing down and this one's sucking up, I think if this is 0.2 and the other one was 0.4, I'm going to be probably seeing 0.6, because this one's sucking up, yes?
Yeah.
This one's pushing down. Now it's easier for this one to go down because this one's sucking up, yes? With that, I am at 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. We had 0.2 on the return, we had 0.4 on the supply. Together they make 0.6 external to that air handler static pressure. Everybody getting that? Kind of cool. You with me, Dan?
Why are you putting such an emphasis on the external?
On the external, because everything that was in that supply was a resistance, wasn't it? The coil was a resistance. Was the ductwork a resistance? Was the grill a resistance? On the return side, that blower's doing, yes? If that grill is very restrictive, that blower's gonna do what? Yes? Resistance higher when the grill. If that ductwork is small, it's gonna go, yes? Higher resistance. It's gonna suck it up even higher, yes? If that supply air static was very small ductwork, is all kinked, that blower's trying to blow through there. What's happening to the static? It's blowing so hard down here, it's pushing this one way up. So my external static pressure is getting higher and higher. Does that make sense? And we said as the static increases, what happens to CFM?
It goes down.
Good. That make sense? Cool. All right. Oh, but we don't use YouTubes anymore because we're electronic men now. Heaven forbid we have to use anything that's non-digital. So we're going to go to digital. All right, so with digital, this is kind of cool. You got a pressure 1 and you got a pressure 2. So if I take one pressure and hook my hose onto that and put it into the supply plenum, it would read 0.4 inches of water column. If I took the other hose and stuck it into the return, it would read 0.2 inches of water column. Okay, here's the tricky part. If I put both hoses in at the same time, one in the supply and one in the return, what am I going to get? 0.6 inches of water column. The combination of the total of all the resistances I have to blow through and all the resistances I have to suck through. And those two give me external static pressure of what that blower is really seeing. What that blower has to blow against, all the duct work, all the grills, all the kinks, all the fittings, all of that, the filters. Cool. Good with this? Nice. Good. Let's look. Oh my God! Look, everything had a resistance. Everything. Look at the grills. Remember that grill, that static that we talked about on the grill. We said we wanted it to be 0.02 to 0.03. Do you guys remember that? Look at that grill, 0.03. That's the static. That's the resistance that air has to go against. If I add that to the 0.02 for the boot, 0.08 for the Y, whatever for the ductwork itself, I do have some resistance in the plenum as well. Is that right? Do I have resistance in that coil? Good. Resistance in the coil, resistance in the plenum, resistance in the duct, all of these add up to the supply static pressure. Return air grill, look, again, 0.02. Nice. Good air through there. Return air boot, I've got some resistance there. The flex duct, look, there's a lot of resistance there. Return air plenum, just a little bit. The filter, I can be anywhere from 0.07 to 0.25. That's a lot right there. So all of these add up to the resistance on the return side. Resistance on the return side plus the resistance on the supply side give me total external static pressure. 0.8. Well, is that good or bad? I like these fittings, and I don't know if you had these on your, yeah, you did. You did have these on there. Look, either point it in the direction of the airflow or where the airflow came from, okay? So it doesn't really matter which way. You've got the arrow that's written on yours right there so you can see which direction it is. Just don't have it at a 90 degree. Because now you're getting velocity pressure on that piece. You want it to be static pressure. So point it either in the direction of the air or where the air came from. Cool? All right, so I got 0.8. Is that good? Is that bad? I don't know. Let's find out. So that is right here because I might have 16 different coils that I'm going to put on this air handle and on this gas heater. Manufacturer doesn't know what coil I'm putting on there, so that has to be calculated in as a resistance. You good? Mm-hmm. Okay. All right. So that's 0.5 on the supply, and I've measured right here, right at the blower, past the filter, and I have 0.3 on my return. 0.3 on the return, 0.5 on the supply is 0.8, right? Good. Never Never do you want to see your resistance on your return side higher than your supply. Because this means it's having to blow through all of that. So the static is going to be higher on the supply side. It's a blower, not a sucker. It was never designed to be a sucker. So if I have more resistance here, the fan is operating very inefficiently. Does that make sense? Cool. So always lower than the supply. All right, so here we go. Here's the same furnace, but instead of horizontal, we're in the upflow position. We're going to measure it right here below the coil, and you saw that all we did was pull the high limit out right there. Pull the high limit out, and you can go in right there. Works out very easily right there. Do it after the filter, before the blower, right there. So external static pressure on this one, we ended up with 0.35 on our supply, and we ended up with 0.15 on the return. What's going to be the total external static pressure on here?
0.40? No. Yeah, 0.50.
0.5, okay, so 0.5. So there we are, right? So 0.5. So one of them had a 0.8 and the other one had a 0.5. We still don't know which one is good or not, do we? Good, so what we're going to do is go to the blower performance data sheets. On the data sheets, where are we going to find these data sheets? On the app? Maybe on the installation manual, right, that we put in? Yes, that's that plastic bag sealed in hermetically sealed stuff that actually, it's like kryptonite to a technician.
It cannot be opened.
Cannot be opened by mere mortal man.
If you open it, you want the warranty.
So when we look at it now, we look up, okay, here's my model number. I'm looking at factory, low, factory, circulating fan, factory, high heat, factory cooling. Okay, factory cooling right there. Look, it's on a high speed there. And we measured those two different furnaces. One of them was a 0.5 static, and the other one was a 0.8 static. And this is off of that 802T blower. We've seen these out there. And on this one, at that 0.5, I'm going to move 1741 CFM on this unit. This one over here, I'm going to do 1625. Well, if it's a 4-ton unit, I'd be okay. It's a 5-ton unit, I'm going to be a little shy, right? So if it's 0.8, what am I going to have to do? If I'm moving 16 on a 0.8 and I have 5 tons of air, what am I going to have to do to this static pressure to be able to get more CFM?
Bring it down.
How am I going to bring it down? What do I have to do to lower my static? How about put the turning vanes in, right? How about straightening out that duct so it's not doing this? How about sizing the ductwork large enough to be able to do getting the air through there? Maybe get rid of that pleated filter that's she got from Home Depot. All of those things are going to reduce this static, is that right? If I reduce the static, I'm good, is that right? Good. All right. So let's look at an electric heater. Where's the coil on an air handler? It's inside the air handler, yes? Does the guy at the factory that's putting in this blower know what kind of coil he's putting in this air handler? He knows. I mean, the air handler, he's building this thing for that coil. So he knows the resistance on that coil already. So when I'm doing an air handler, I'm going to do external to the cabinet of the air handler. But on that gas heater, I had to do external to the gas heater, but I had to include the coil because they didn't know what coil that was. Does that make sense? Cool. All right. So let's do this. Let's put this in place. And I got a 0.4 return, and I have a 0.3 supply. What is my total?
Calculators.
I think we got this one. I think this is simple math. What you got on that one?
0.7.
0.7, right? You guys with me? 0.7. What's wrong with this?
The return is greater than supply.
Oh, I got more resistance on my return than my supply. So this is not a blower, it's a sucker. Was it ever designed to be a sucker? No. Maybe he's pointing at you thinking you're gonna be a sucker. So what, where's my problem on this setup?
Return.
It's on the return side. Does that make sense to you? Good. What am I gonna read on my meter? If I'm looking at this, what am I gonna read on my meter? Total external static.
0.7.
0.7. All right, if it's 0.7, I'm going to look on here and it's going to say, okay, well, this is the furnace we have in there, and I'm going to go across to here and it's going to say high speed 0.7. Well, high speed on 0.7, my goodness gracious, we're only doing 1120 on that thing. The CFM is 1475. This may not do very well at all because this is a
4 ton.
4 ton with 1400 CFM. And look at where it's at on the chart. You see the chart go any farther? Mm-hmm. What does that mean? We're already at the high end of this thing, right? Good. Where's our problem? You've already discussed where our problem was. It's on the return side. So if I make the return air larger, I get a better filter, I do something on the return side, what's going to happen to the static? It's going to drop back here. And what if I get it back to a 0.5 on here? What's going to happen to my CFM?
I'm going to have a blower then.
I've got 1687 then, right? How am I doing on a 4 ton now? Sweet. Does that make sense?
Yeah.
Can you figure this out? Can you figure out where the problems are using a manometer? You have a manometer? You like it? Good for you.
And you got an app.
And it's got an app. That's right.
And it's what? It's free. It's free.
Just swipe it up. All right. All right. So, wait, what kind of manometer do you have? Digital Bluetooth. Works out well. These are great tools. I really feel very good about it. What I like about this is it's not just 2. You can add more. And as you add more, I can see the pressure drop across the coil. I can see the pressure drop across the filter. I can see the pressure drop across the supply plenum. I can see all of those on my deal. Is everybody okay with that? Cool. All right. So the app is nice. It works out good. You can do all the different. So let's see what happens here. This is called, let me start that over again real quick. All right. CFM using the sensible heat formulas. Now this is a great way for you guys to be able to actually figure out how much air am I moving just by turning on the heater. Okay? If I know that I have 240 volts that I measured, and I have 97.6 amps that I measured with my amp meter, multiply that by 3.413 because that changes watts to BTUs. I'm going to be putting out 79,000 BTUs. Divide that, volts times amps times 3.413, divided by the temperature difference between the supply and the return. 50 degrees. It's 70 degrees going in and 120 degrees coming out. 50 degree temperature rise. 50 times 1.08 comes out to 54. So if I take the BTUs divided by the temperature rise times 1.08, it'll give me a CFM of 1481. So just by taking a few calculations while y'all are doing a heating maintenance over there, you can find out what the CFM is. If I'm doing a heating maintenance, that means it's winter time. When do you want to change out ductwork? Winter or summer? So every winter, if we are doing a heating maintenance, you're already checking the volts and the amps. You're already taking the temperature rise on the supply and return. I've given you everything you need to have right now to find out what the CFM is. How great is that? If I find out that the CFM is low because the ductwork, now's the time to be changing it before the summer hits. You don't want to be changing out ductwork in the summertime. Let's do it now when we don't have a lot of work. Does that make sense? Cool. Can I do that with a gas heater? Yep, same thing. Same thing. If I have 100,000 BTUs of input and it's an 80% furnace, my output is 80,000. So again, 80,000 divided by that temperature rise times 1.08 gives me 1481 CFM. You like this? Good. It's a good way to calculate the CFM that's coming out of that system. Or you can go to the app, and with the app, if it's CFM with an electric heater, talk to me, Hunter. If I have CFM with an electric heater, all I need to do is plug in the volts, I plug in the amps, and it automatically calculates total BTUs. Put in the temperature difference between the supply and the return. I did all the 1.08 behind the scenes, and it'll tell you the 1481 CFM that system is actually moving. Would that be golden for every heater maintenance call you guys are doing? Because now you can find out how much air is moving during the summertime when it starts getting bad out there. Does that make sense? Do the duct changes during the winter. This is doing it for you. If it's a gas heater, I have the same thing for you. Use the heater, check it out. You're doing all the stuff already, you just haven't put it into the calculator. Cool?
Cool.
All right, one thing here, when you're doing this, change the heating and the cooling speed around so you can run the electric heater on the cooling speed,
Which is high.
which is now you know how much I'm getting in cooling as opposed to when it's running in heating, because then it's going to be less CFM.
Right.
If I want to know what I'm going to be moving in the cooling mode, just turn them around. Does that make sense?
Yeah.
Good.
Makes total sense.
Easy?